We'll get started. So, wish you a very happy new year. I hope you had a very good evening and a mini blast, whichever way, for celebrations. So it's good to see many people today live. Great. So we have Dr. Petri Piiroinen is a applied mathematician. He studied, all his PhD in Stockholm, and he's in the National University of Ireland. Petri is very popular in Galway. NUI Galway is very, very popular with students. And we met in 2007, and the first time he was doing something on dynamical systems, and I was rattling something on economics, and he got interested, and then we started our collaboration. 2007, he used to organize a thing called Modeling Forum, like PhD students and interested people, every Tuesday lunch hour talk. So he had invited me to give a talk on economics, and he got really interested. So I slowly converted him into a post-Keynesian economist. So as you will see.
Well,
and,
not yet.
Yeah, but he was very kind when I told him about this, and I wanted him to come and give us, participate and contribute. And he was extremely, forthcoming. And even though it's a Christmas holidays, and I told him he might be lecturing on a Christmas day or first of New Year and all that, he said, fine, that's all okay. He was very enthusiastic and supportive. And I'm really grateful to you, Petri. And thank you for taking your time. And I hope you will enjoy this lecture, and the next one will be followed by Vishu as well. So you will see the connection between them and what we were talking before. Thanks,
Okay.
Petri.
Thank you for the introduction, and thank you for inviting me here. It's India is an amazing country, and it's always fun to be here. And Happy New Year to all of you as well. This is the first for me, in the beginning of the year with a lecture, so that doesn't happen. It's probably the last time as well. Who knows? Well, anyway, so as Rega said, my background is in applied mathematics, and so I've been learning a lot about economics these 8 days as well, and in some sense, and I'm by no means an expert in those fields. So if someone has a nice economic interpretation or something they want to highlight in terms of economics, feel free to do that. It's just great to interact it. So I know that a lot of you have never really dealt with nonlinear dynamics at all. So how many have done any nonlinear dynamics? Okay, so quite a few. So what I will do is, so my idea with these lectures is to really start from the beginning, right? And slowly build up. So hopefully at the end of the day, I can say something about bifurcations, something about transitions, and something about catastrophes, so that tomorrow Vishu can then take on there and talk about some of the models and some of the economic systems that they have been looking at. So that's my idea. And then I'll also try to throw in a few examples every now and then. So just to go back to what I did when I was a PhD student. So my background is in mathematics and numerical analysis, and then I did my PhD in mechanics, which is sort of a bit unusual in that way. So I worked on models on 2-legged walkers. Okay, so these guys are called passive walkers. The only energy input is energy. So they walk down inclined plane. So the only interaction with the environment is, gravity and also the feet to the ground. So now you might wonder, why is this of interest in a meeting on economics? Well, at that time, I didn't realize that I learned a lot about dynamics, a lot about interactions, and a lot about crashes as well, as you will see here in a minute. And so ever since modeling in general and be able to analyze models have been of interest. So you will see here, there are 2 walkers here. One of them is just free to walk down this plane, and he has just undergone a bifurcation so that he will be swaying back and forth more and more. I'll show you from another angle, and then eventually fall. Okay, so that is a very catastrophic event. So what really happens here is that he hits the ground, foot with the ground, and then falls. So that event is nothing that you would be able to see within the dynamical system. There's no differential equation that explains that I'm hitting a boundary that is outside the model. Okay? So that is a atypical event that you will not really see in normal textbooks. Right? So about discontinuous changes. And then the second walker we have here, I'll just rotate this if I can. So you can see it's really swaying back and forward. So what it's actually trying to do is to reach a quasi-periodic attractor, but it goes out of hand. Well, the second walker, you can see here, there's some, the foot turns red every now and then. And what I'm doing there is just to implement a very simple feedback on the feet, so that, because I'm able to calculate the stability of these some periodic orbit. So what I'm doing is stabilizing that periodic orbit while changing the ankle angle slightly, which means that I hit the ground at a slightly different time that I did before, and thereby stabilizing the otherwise unstable gate. And I can walk past. So in these mechanical systems, which are that are easier to model than economic systems, but everything is there. You have the rapid changes, you have the feedback loops, you have the complex dynamics, and so on. So, as long as you can do what I do, collaborate with someone in a different field, you can then come together and try to interact and come up with some kind of solution. So that's really where my interest lies, looking at models and systems and see if I can make any sense of it. And then also, I also like numerical methods, so be able to highlight this, maybe with a little movie like this or something like that. It's really important for me as well to be able to show what results actually mean for an audience who cannot look at an abstract equation and see. So, before starting, just so some of you have asked, where is Galway? So here we have Italy, Spain, France, Sweden, where I come from. And so we live just on the west coast of the world, really. And the whole Atlantic is pounding us with bad weather all the time. So I looked at the news yesterday, another day of bad weather and 90 kilometers per hour winds and rain and that kind of stuff. So being in this climate is fantastic. So another reason for coming here, not only for the science but also for the weather. Anyway, so just to go back to the modeling aspect, I will say something about that which I find is of importance. So a lot of what you have been talking about here for the last week are you try to model the world somehow, right? To be able to make some kind of sense. So in mechanics, it's quite deterministic. It's easy. You have the forces, the joints. It's relatively easy to put something in the context. You write the differential equations, Newton's laws, and then everything is you have a nice model. And then if you want to, you can add a bit of noise to it just to see how robust it is or something like that. Okay. So as I said, I've been working on walkers. Similarly, I've been working on problems on gears, which again have impact. They're quite straightforward. So I'll show you some models, not because of the mechanics, but because of the behaviors they can show and what you can expect when you have switches. Okay. Another simple model, which is just friction model, again I'll come back to this. With this mass on a belt and friction affects it in different directions depending on its movements. Again, quite relevant for when making for policy decisions, because you're making very rapid changes. You do this one day and then something else the other day. So of course your system will immediately switch to something else. So if you look at it from that point of view, which is my dynamical systems point of view, then I think it's important. And then this is another thing I've been working on, which highlights a bit of the geometrical aspects that I'm already interested in. I'm working with some psychologists on decision making. So they have a simple game here where you have to choose one of two things, and then on the computer screen you move your mouse into those things. However, what was an abstract idea for psychologists was to say, can you look at this way of making decision as living in some potential field, on a potential surface, so that you're attracted down to one of these wells? That was a sort of an idea they had, and so they had a lot of data, so why don't we build those potential surfaces? So that's what we did, and that really, you can then highlight how the surface changes how you learn. Right? So, and that again by using ideas from dynamics, but in a completely different field. Typically, what they do is they have a lot of data, they do statistical analysis, which is fine, and they get results. But here you can also get some visual impact. So if you want to make an impact in a different area than mathematics, so I think it's important to be able to visualize for that audience what you actually mean, with your changes, even though you lose a lot of the rigor and the importance. But so that is sort of where I come from. So at the end here, I've updated these slides a little bit. I found a few typos and mistakes. So I guess I can send the new versions to some of you, and then you'll upload them. So at the end here, I have a long list of, by no means an exhaustive list of references, but something that at least somewhere to start. So another important thing to think about here. So here are two time histories from geology. So what do we have? No, that's from, I must have, so that is the US stock market. So we've seen, Garrett showed some of these pictures. So we see that there is some kind of trend in the same way as we were talking about trend in the stochastic models, and then you have stochasticity about that trend, but also you see very rapid jumps. So the question is there some way in which we can model the trend through a dynamical system, and then the question is, how do these rapid changes happen? Is it through a transition that can be explained by dynamics, or is it through stochastics, or some random event that we can't really affect? And the reality is probably somewhere in the middle between, because some are completely random, like a discontinuity, which is important. However, if we then look at things like the Earth, so this is the CO2 content concentration in the Earth between thousands from 800,000 years ago up to now. So here we can really see there is a nice periodic motion underlying this on top of these, and then we have noise on top of that, which can depend on a lot of different things. Where you take your sample, how accurate your how accurate you are, and so on. So unfortunately, we have had a nice oscillating here. Unfortunately, in the last very short amount of time, 50 years or so, we can see the CO2 levels are really going up in Earth. So of course that's the worrying thing here, that we are so out of what has happened before. But is there some way in which you can explain these rapid changes? So hopefully some of the stuff I'm going to present will fit into that thing. However, there are also some things that should be quite regular. So do you know what this is? The heartbeat, right? So that is a beautiful dynamical system, quite complicated, but it should be quite regular, and more importantly, you have very rapid changes. It's still for a while, and then do. And that is, of course, has to be forced by something, or the system itself has to be periodic, and then you have to have these. So these are called sort of slow, fast behavior. So nothing happens for a long time, and then there's a fast, rapid movement, and those can be explained. That kind of motion can be explained by just standard, ordinary differential equations with no special behaviors. And then, of course, I just took it out how the depth to GDPA ratio has increased in so this is in UK and this is in Ireland. So you can see after the crash in 07, 08, it all took off. That is purely because of policy decisions, right? So at that day, okay, the economy is not doing very well. The policy decision is to buy up the banks, and then of course that will affect that decision. And in Ireland, I don't know what they call it, the black night, or the night before the black. Yeah. So what happens? What they have sat in this room for many hours, and then they made the decision: we'll buy up all the bad debt, all the banks, and then of course our country has, where we live, Ireland has felt this since that day through austerity. So if a different decision had been made that day, we would have gone down a completely different route. So that is a really discontinuous event that changes the course of the future. So this is discussed every day not every day, but very often in the media, what actually happened that night in that room, what people were involved, and what did they talk about. So I don't know if we will ever know. The finance minister, unfortunately, is dead, so he can't say what his thoughts were that day. So, and the record keeping is a bit so and so. Anyway, so this is just putting you into perspective. So I want you to ask a lot of questions, if you can, about dynamics. So I will be a bit more technical here for a while, not extremely technical, but more. So this is sort of my background. So when I think about dynamical systems, okay, I think about equations, but also try to take a step back. Even if this doesn't fit exactly my model I'm working on, what does it actually mean? What is the dynamics trying to, what kind of dynamics do we have here, and what can we say about it? Okay, so this is roughly the outline of the day. So we'll see where we land. Depends a little bit on how many questions we get and so on. So dynamical systems analysis, what is beautiful with that is that a lot of the results from linear models can actually be carried forward through some really nice theorems to show that there are similarities within, or there's an equivalence locally between linear systems and nonlinear systems for equilibrium points and so on. So that means that you can analyze a linear model and then draw conclusions of some aspects of the nonlinear model. So therefore, I'll spend some time in linear systems, then I'll introduce nonlinearity. Then an important thing with bifurcations are, of course, stability. So Vish already started to talk about stability yesterday, and essentially what bifurcations are is change of stability somehow. Something changes, or the qualitative behavior of the system changes somehow. And that is really, so we'll go through that, and then bifurcation and transitions, and then I have a few examples. So we'll see where we are at the end of the afternoon, and so on. Okay, so a few more things about modeling. So this is how I think about modeling, right? And dynamical systems come to play. So of course, we have a real-world system. We try to understand it. We have a mathematical model. We have seen a lot of different types of models this week, so that is great. So we try to understand something about the real world, and also we try to simplify things so that we can actually get something. We try to get hold of the underlying behavior, be able to say, so why is this happening? So get rid of all the things we're not interested in, just look at what we're interested in. And then on top of that, if you want to do like me with the walker, you want to develop numerical methods for this, okay? And hopefully there is then a feedback to what your output to the real world, and see, something wasn't quite right here, or we doesn't understand everything here. So maybe there is something wrong in the modeling, or maybe you have to go back to the real world and find other types of data that fits this picture better. As I've understood it, in economics, this can be very tricky because companies, banks don't give out all the data they have. So you can't really know when policy decisions were made, maybe, or so on, okay? But if you're pure a dynamical systems analysis, what often happens is that people have spent years developing a very good numerical tool. Maybe in econometrics it's the same idea. We know our tool really well. Now we need to find a mathematical model so that we can use that tool and to publish papers so that we can stay in our job, right? And then what we really would like to do is also to change the real world to fit our numerical model. And that, it happens over and over again. Everybody does it to some extent so that we can, we have to publish papers. That's a part of our game, but also we are interested in to know how far we can push our models or numerics that we have seen and see if we can find. And then, of course, from a purely mathematical point of view, it's often here where a lot of interesting equations are born that they then take their own route into something else and become a very theoretical, affair in itself, and then leaves this realm altogether and starts its own world and maybe something new and conferences just dedicated to this type of equation and so on and so forth, which is fine. But I think it's just important to not forget where you are in this scale, what you actually want to do with your tools and your methods. But that does happen a lot often. You try to squeeze into reality into your result. So one has to be a bit careful about that, I think. Okay, so let's start with a bit of mathematics. So just to introduce some notation. So we have seen a lot of notations already. So essentially I will call my variable x, could be in one dimension, n dimension. I'm a bit sloppy sometimes with saying writing down what the dimension is. So if something is unclear, please ask me. So I use the dot notation for the time derivatives. If something dimensionally is not obvious, I typically use column vectors for states x. And then I write fx and ft for something like that for partial derivatives. And also an important matrix here is the Jacobian, which is so if f is n dimensions and x is n dimension and f is n dimension and x is n dimension, then the partial derivatives in all functions and variables, Jacobian. So that is important. That forms the basis of all stability analysis. A transpose. It's just it's just transpose of the vector. So again, if there are some issues with notation, let me know. And then the type of differential equations, I'm assuming that it's possible to write the differential equations in this form. So without, just think of it as a change in time, like Vishu said yesterday. Okay, so if you have time and we have x, so if this is x of t, okay, so then at each point, the tangent is x dot. So that's really the slope, the speed in which we change. Okay. What else can we say here? And similarly, so I'm mainly going to focus on differential equations, but I will also sometimes take a step into the discrete world. So there was a little bit of discussion about discrete models yesterday, and the fact that in 1D discrete models you can have very complicated behaviors and chaos, while in one-dimensional ODEs you cannot in chaos. And it was sort of highlighting, but see if I find the picture. So basically, this is how I think about it. So assume that you have some motion, okay, and there are trajectories. Let's start from xk, and then and so on. So this is some kind of trajectory in this solution space. So one way to look at it is to introduce something called a Poincare surface, so an Poincare map. So that basically means somewhere in my space I introduce some surface, and every time I get there I collect that point, and then I go back, and then I come back, to that, and so on. So that means that we can. That means that we can introduce some map P, Poincare map, that takes us from that surface back to the surface again. So what you see here is that even if it has very complicated dynamics away from the surface, the dynamics of that trajectory is captured by that map. Okay? So that also means you reduce the dimensionality by introducing this surface, because you live on this subspace. And that means that you can have complicated dynamics here, but you're projected onto this plane. So that means that you can have, if you have chaos in the original system, then you will have chaos in the map, in the maps in the discrete system. So that is why there's slight difference between maps and this, differential equations. That also means that if you have a periodic orbit or limit cycle like this, that means that corresponds to just one fixed point on this map. So a fixed point in the map I think of often as a periodic orbit itself, because that means something has happened and now I'm collecting. So this index here could correspond to day or year, or depends on what you're looking at. The problem is, if there is not an obvious, let's say once a year, if there's no obvious period in your system, then it could be hard sometimes to find a surface that you will always reach. Right? Imagine you have a 100-dimensional system. How do you place if you have 100-dimensional space, how do you place your code surface in there so that you know that I will regularly get there and pick up something like this? So in general systems, which is not the one we have, then that is a hard task itself. But often, the system we're looking at, there are some obvious things. Something is oscillating, that means that it has a maximum and minimum. You can always pick those things up. Or something is time periodic, like the year, so then we look at the system once every year, or something like that. So then that means that because time is always moving forward, you will always reach that position in time. So it's just a way to think about discrete versus continuous, which I think is important. So again, what Vishu said yesterday, so clearly, if our system is not changing at all, so our time derivatives are zero with respect to all the variables, then that means that so if this is true, that means that nothing changes. That means that the right-hand side here, which I call the vector field, if I mention something, I call that vector field. And what is a vector field? It's good to point that out as well. So if x1 and x2 here sort of highlights the whole space somehow. So vector field is that at each point in that space, there is a given direction that you can take all the time. So if you move to another point, you might move something else, and here you move like that. So that means if I have a trajectory, you have to follow the vector field, so to speak. So it's like think of it as a stream in a river. If you put something in the stream, you just have to follow the stream. So you might have whirls, so you have to roll around there, and then so on. And then, of course, a equilibrium point is then when these arrows have zero length, right? So that means you're stuck there. So when you look in the literature and you look along, so for the sake of this talk and what I usually do, when I have continuous systems, I call them equilibrium points. And when I have discrete system, I call them fixed points. So just to highlight, sometimes you hear people using the words indifferently, and that's fine. It's just that I try to use, so it's clear in continuous system, I have an equilibrium and fixed point in a discrete system. Also a slight difference. So as I said, the vector field has to be zero for an equilibrium point. For a fixed point, we have to map back to ourselves. Right? So that, which is like this picture, I'm mapping back to myself. So that just requires slightly different type of analysis when we actually find the fixed points and the equilibrium points. So here we have to solve this equation, and here we have to solve that equation, which is sort of slightly different. So something to think about. Any questions so far with the basics? Yeah? Yeah, so let me do a small example. Right? So x dot 1 and x dot 2 is equal to, I don't know, let's just do something like this, x plus x2, and then we have 2x1 plus x2, say. Yeah? And then let's say we look at, this point is 1, 1, okay, so we have a point 1, 1 here. Yeah? So then x1 dot of 1, 1 and x2 dot of 1, 1, what's that? That's equal to 2 and that's equal to 3. So that means that I'm moving with a speed 2, say, in my x1 variable, and speed 3 in my 2 variable. So that means that I have to go, so moving 2 there and 3 up. So it will look something like that, right? So that will be my direction exactly at that point. But that can, of course, change all the time. Yeah? Yeah, so of course, so if this is in many dimensions, then you're sort of moving, then you have an n-dimensional vector that points you. Is that clear? Yeah. So think of it, as I said, think of it as a stream. So every place you are, there is one direction. So of course, if your vector field here is nicely behaved, differentiable and continuous and so on, then trajectories in this vector field, following this vector, can never cross. And they cannot cross because that would give non-uniqueness. Right? Because if you could cross yourself and the direction was like that, if you're at that point, that would mean you can determine your future. And most systems can be determined. Okay. What we'll see, some of these discontinuous models have different behaviors, and also these when vector field is nice, then you can always move back in time as well, usually, so you can get to where you were and along the same trajectory. Yeah. Which the graph that you said about the Poincare map? Yeah. No. Okay, so the Poincare map. So this picture sort of says it all. So let's say, so if I do can you see if I write here? Yeah. Okay, so let's say we have x1 and x2. Let's say we have, so let's say I introduce a Poincare section, like that surface here. I put that at x2 is equal to 1 here, okay? So I introduce, that's just a surface. So now I will start on that surface, and I have a vector field in x1, x2. So then I will follow that vector field, so it might look like this. The vector field might look like that. So then I'm following here, and then I'm coming back. So then this is my x0, and then this is my x1. So that means now I can write a map here, how I got from x0 to x1 in the discrete way instead. So now I'm just looking at points on this surface instead. So that's how, right? Is that sort of somewhat clear? Yeah. So if you're lucky, you can write down an analytic expression for this. So then, of course, it's much easier to work with this than have to solve your differential equation, all the time. So then you can throw it into a computer, just iterations, which is much, much easier and faster. So there are lots of benefits. But of course, you will lose everything about what happens up here. So if I'm coming in with some surface here that the system itself doesn't know, then I can't. So you lose win and win some. So modeling is a little bit like art. You get a feeling for what works and doesn't work. So that's that.
See, using these vector field directions, we can actually construct the map.
No, I'll come to phase diagrams. I'll come to phase diagrams later. Yeah.
So you can always think of this in terms of economic variables.
Organizations make statements. So every month they look at what is the unemployment in the country. So now it's 1 million, now it's 1,100,000, 1 million, and so on. And then they try to use this as an estimate. So you have 3 dots, and it looks like a linear growth. Okay, then we assume that, then we can, from those 3 dots, we can build a linear map that takes us, that kind of, so it's used in a lot of different ways. That is a trivial way, but it doesn't. But of course, the dynamics of the unemployment and the employment force is, of course, extremely complicated. So that's why you take snapshots and try to get some estimates of this. So there you reduce a massive system to 1 dimension. So you will clearly lose some information there. Like if a company between two of these dots open a really big branch with 5,000 employees, then of course it will go down and your model will never be able to pick that up as such. But no. So I'll come back to this. If you have questions, just so this is the basics. As you see, what I'm trying to convey here is the principles. I don't want you to be able to solve differential equations and so on. It's the principles and after. Okay, so yesterday Vishu showed you this simple equation from growth, and we'll probably see growth tomorrow as well, Vishu, I suppose. Yeah. So if we know some initial condition at some point, we have this linear equation, so 1-dimensional, and then we have an exponential solution, right? So, oh yeah. So that means that we have some time t0, we have x, we know what our x0 is at that time, okay, and then we evolve from there. So you can see, ignoring the a is equal to 0, because that means every point is an equilibrium point, which you can have in such special cases. But you see that what happens to x0 depends on for x, starting at x0, depends on one thing and one thing only, the sign of a here. Okay. So if a is positive, then we either go to plus or minus infinity, depends on the sign of x0. Right. So in that case, we go to plus or minus infinity if a is greater than 0. Or if a is less than 0, then we have exponential decay to 0. Okay, so you see here, this the parameter in front of this term is what determines the future for this. Okay, and so we will see later the analog of this number here is eigenvalues of the Jacobian matrix. So it's just the same kind of thing, but in higher dimensions. So you can think of this as the A here is the eigenvalue of this 1-dimensional matrix. So eigenvalues really important. That's, so that part of linear algebra is key here. Similarly, if you have a discrete model, then the system looks like this. So again, we have exponential growth, but A comes into play in a slightly different way. So what values of A here will now give decay down to 0? At less than, yeah, so between two values. So the absolute value of A has to be less than 1, right? So that means that so again, something Amit sort of pointed out a little bit yesterday. So assume we have xi here and xi plus 1. Oh, sorry, I'll do it another way. If I put k here and xk, okay. So if A lies between 0 and 1, so we have our x0 here, okay, and 1. Then we start here, and then we decay exponentially like this. So that case would be if, yeah. But if A is negative, what happens is that we get the first point here, the second point will be here, third point there, fourth point here, fifth point. So you will oscillate between plus and minus the value. So this was what Amit was talking about yesterday, that because we have a discrete model, we don't have to go through anything, right? We just land somewhere else, and then we land something else. So you can oscillations even in a very simple model like this. So oscillations there is sort of equivalent to here. So the important thing here is to look at, okay, we have exponential behavior locally for both these types of models, and that is important. So the fact that we change exponentially. Any other questions here? No? Okay, so now let's lift it to 2D, which essentially we can then lift to ND quite easily. It's the same principle that applies. Okay, so I'm going to use, so in a linear model, we can write our differential equation in this form. Okay, so from this, which we have there, okay? And an equilibrium point, in this case, when we don't have any constant terms to the right, unless if A is well behaved, which means that the determinant is non-zero. If the determinant is 0, that means that maybe A is equal to C, B is equal to D, or something like that. That would mean a sort of, it wouldn't be a proper two-dimensional system. You have some of these kind of degenerate cases. So that means that if we don't have constant terms, then the equilibrium point is 0, and there's only one equilibrium point. In linear systems, only one equilibrium point. If we do have constants, we can very easily make a variable change that takes us back to this example. But if you want to, I can do that calculation, but this is quite trivial. So that means every linear system you can rewrite in this form that gives us this matrix A. And so now we can use that matrix for our analysis. So think of this as the analog of our constant A, or our one-dimensional A here. So now we have a matrix that has exactly the same principle, accessed in the same way. Okay? So a little bit of differential equations theory here. So from now on, and most of the time, I will just assume that T0 is 0. Yeah, so it makes it easier to write. So I don't have to write T0 every time. But you can see it's a general thing. Whatever time you start with, you can, and some initial condition there. So a general solution to a linear model like this can be written as a linear combination of linearly independent vectors. So what does that mean? Well, it means that you have these vectors, and it spans your whole space. That's the whole thing. So that means you can get everywhere in some sense. Okay? And the C1 up to Cn, should be Cn there, should be, you can find through the initial conditions. Okay, should be small x there as well. Okay, so the good thing now, because everybody has studied linear algebra here, right? So that means that the good thing here is now that we can find such vectors relatively easily if they exist, and that means we can use eigenvectors for this. So if we can find eigenvectors that span the space, then we can use everything from the matrix A to span this space, so we can get anywhere. Okay, and then we also have n eigenvalues that corresponds to those eigenvectors. Right? So that means we can use these as these linearly independent vectors. We can use the eigenvectors and eigenvalues. I will call them W, I think. Okay? And of course, to find the eigenvalues, we solve this equation. Right? So everybody remembers that from the linear algebra course. And I is the identity matrix with the right dimension. Okay, so now there are three different cases in 2D that can happen. Okay, we can have that lambda 1 and lambda 2 are distinct real. Okay, they can have the same value, or they can be complex conjugate. Okay, so you can see the solution for two distinct real. Again, you can see now we have so these are our vectors. So in 2D they would look like x1. Oops, not red. So they would look like x1, x2 of t is equal to some c1, one vector e to the power of lambda 1t plus c2 and a vector e to the power of lambda 2t. Okay, so those are now our two eigenvectors. So see what happened here now. So if you look at those terms and look at this model, the solution of this model. So now we see that this A here has the same function as the eigenvalues now have in the solution. So if we have two negative eigenvalues, lambda 1 and lambda 2, that means that the solution will go to 0. Yeah? And if one of the lambda 1s and lambda 2 are positive, okay, so if one is negative and one is positive, the negative one will go to 0, and the other one will dominate. Yeah? So that means that only the case where both eigenvalues are negative will we have a sort of a stable trajectory going to 0. I haven't introduced stability yet, so I'll try to avoid using that term, but will go to 0. Yeah? And then this, when lambda 1 and lambda 2 are equal, it's a sort of special case, so I'm not going to dwell too much on that. The thing is, again, it's this eigenvalue lambda, which is equal to lambda 1 and lambda 2, that determines if this goes to 0 or not. Okay? And then finally, if you have two complex conjugate solutions, so then the solutions will look like that, and V has now a oscillatory term, right? So if we take one of the eigenvalues, lambda 1, we can write that as a plus IB, which is in a complex plane. So this is the real part, the imaginary part. So we can see when we use all the theory there from complex analysis, not all theory, but some theory, then we see that the real component ends up here, and the complex component ends up here. So you see that, again, whether the solution goes to 0 or not depends on if alpha here is positive or negative. So if this is negative, then this term, if alpha is negative, this term goes to 0. That means everything goes to 0. Similarly, both goes to 0. So what that means in real terms here, is that if we plot one of them, t, and if we plot, let's say, x1 here, then we have oscillations to 0 for the real part of lambda I equal to alpha is less than 0. Yeah? So now you can see how important the eigenvalues are for the solution. So go back to think about the models you are thinking about. What type of behavior do you see? Does my model oscillate? Does my model, go often straight to some sort of steady behavior, or what happens? Yeah.
The example is the Samuelson multiplier-accelerator model. So you can think of that. It generates all the dynamics. So when the accelerator coefficient is on the x-axis, MPC, marginal propensity to consume, on the y-axis, fix MPC at one value, 0.5, then move the accelerator coefficient. Very low values, less than one value of accelerator coefficient, you will have monotonic convergence to the equilibrium value. And certain interval, it will damped oscillation. It will oscillate, but it will converge. The C, area C, is the damping but explosive, because that alpha is positive. And then the fourth region, D, is just monotonic explosion. So that's a classic example for this problem. Yeah.
And also, this is a differential equation. That is a discrete problem. So you can see there's the same ideas that cross over from the discrete and the continuous world. So, okay, equations are fine, but unless you see in your head or with your eyes what's going on, then that's when you introduce phase plots, and that's why someone mentioned already. So now we can try to visualize what this might look like. So there are three different cases corresponding to this guy when lambda 1 and lambda 2 are distinct real. Okay, so W1 and W2 are the two eigenvectors. Sorry. So it should be x1 and x2. I used an old slide here. So there you can see. So the direction of one of the eigenvectors is like that. The other direction is like that. So they cross exactly at the origin. Okay. So and what happens here is that if you start on exactly that on the eigenvector there, then you will stay on it for all time and go back in. So this is what is known as a stable manifold. Okay, so in this case, we have two. So this is one stable manifold, and this is one stable manifold. So in a two-dimensional system, we have two stable manifolds. Okay, for the case when lambda 1 and lambda 2 is negative. If they're both positive, you can see now we have like this and they're like this. Oh, I forgot to say, because lambda 1 and lambda 2 are negative, we know that we are approaching 0 because the exponential term. Right? That means that then the arrows will point inwards towards the equilibrium point that we are analyzing. Similarly, in this case, the two eigenvalues are positive, so the the directions are pointing outwards. Okay, and then this is another interesting case because Amit mentioned yesterday about chaos, that you get close to points all the time, and I'll come back to that in a second here. So in this case, we have one stable manifold because one of the eigenvalues is negative, and an unstable manifold because one of the eigenvalues is positive. So that means that we have one stable direction and one unstable direction. So what Amit meant yesterday when we talked about this was that so you come infinitely close, very close here, and then you get thrown away because you can't cross any of these lines. You get close here, then you get thrown away to another one of these saddles. And then you get close to that, get thrown away, and so on. And because there are infinitely many of them in the chaotic system, then you get thrown back and forth between such points all the time. Yes?
Essentially, you are solving two systems of linear differential equations, right? And you obtained two eigenvalues, lambda 1 and lambda 2. No, I want to go to the graph you showed, page space. So for each corresponding lambda, we'll have an eigenvector. So why are we seeing two directions? Actually, more than two. So what are these two arrows?
I'll come back to the trajectories in a second.
Okay.
Yeah, that's a good question. I want to start with the manifolds, and then I'll come back to the directions. So just okay. So let's start with the stable one here. Okay. So I have two directions: stable, 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 stable. Okay. So let's assume now that. So if this is W1 and this is W2, right? So let's assume that lambda 2 is less than lambda 1 is less than 0. So that means that lambda 2 is smaller than lambda 1. So if you have this type of solution, which of the two terms will go to 0 first? Both are negative. Yes, so the smaller, so lambda, the direction, so this guy will go to 0 first. So that means that if I start with an initial condition here, that means that the lambda, this direction, will go to 0 first. So that's why I'm making a turn, right, like that. Right? So if lambda 1 and lambda 2 are very close, then you get like a star shape because you hardly move at all. So that's why these trajectories here, just to highlight that one of them is slightly smaller than the other. So yeah, so this, what this can, if you look at this in a sort of time history, okay, my trajectory there. So I started, so if I just looked at x1 here, I started at a positive x, and essentially I just somehow went to 0. If you actually look at it as a time history. But if you look at the x2 instead, I'm starting with a negative x2, then I'm going slightly positive, and then I go to 0. So you see, even if you can see these kind of overshootings in trajectories in linear systems, what it essentially means is the relationship between your eigenvalues in your original model. So you can get hold of a lot of information because time histories are good, but they don't give the whole picture. You really need to look at it in the phase space to actually get the geometric picture of what's going on. Okay? So dynamical systems is all about geometry and trying to look at it. So similarly, if lambda 1 and lambda 2, if one is much bigger than the other, then it go to infinity faster than the other. And here, so one will go to 0 and one will increase. So that's why we get one go to 0 and then we go up. Okay. So these are interesting cases. This is a degenerate case. I'm not going to discuss. It's the same idea, but here we only have one direction because the two eigenvalues were the same. So you might have just two copies of the same eigenvector. There are other cases as well, but I don't want to go into all the degenerate and special cases because it works no purpose. The other part that is more important is the oscillations that I show there. Okay? So now there are three things that can happen in a linear system. We can have, if your real part of the eigenvalue is positive, so remember where that came in here, that means that this term will grow out of bounds. That means that we are spiraling outwards. So we can have, so the direction of the spiral here depends on the coefficients A, B, and C, D. Right? So that depends on what they look like. So you can have anti-clockwise or clockwise spiraling. Okay? So all these are mirror images exist. And if your real part is negative, then you will spiral into the equilibrium point. And exactly at 0, you will see e to the power of 0 is 1. So the only thing that remains is just the cosine and sine terms. And of course, they will not neither decay or increase. They will just oscillate. So that means we will get limit cycles like that, or periodic orbits like that. It's not a limit cycle exactly. So we can have that case in time history. We can have that case, or we can have should be the same height. So a big family of problems that people look at that only has spirals like this or saddles that is this is Hamiltonian systems. So Hamiltonian or sort of energy conservative systems is a very popular big research area. And a lot of the economic models, particularly the macro models that have, where you have a closed economy, fall into this part, right? Where you either have, periodic orbits or you have saddles. Okay? So you look at the, I don't know, something that is conserved in the system. Maybe you can highlight something on that.
Models, the way you get saddle points because of Hamiltonian systems. So the assumption that actually takes you to the equilibrium point is the rational expectation equilibrium. So if you're outside the equilibrium, you exactly jump on the stable manifold, and then you'll reach the equilibrium. And that's what the rational expectation assumptions mathematically does to you. So if you relate to growth models, human capital model, learning model, rational expectation, learning model, they exactly anywhere outside, they jump exactly on the... And there is one class of models called overshooting models. Don Bush, 1976, you might have studied the exchange rate overshooting models. You'll see they discretely jump onto the saddle, the stable manifold, and then they'll reach the equilibrium. So it's the mathematics. This is the basis for most of our economic systems. Equilibrium, general equilibrium theory, and also economic growth models. Yeah.
Any other questions here? Which one? This guy? That one? Yeah. So maybe hold that thought for a minute. I'll come back to that just in a second, because now now we have these three classes of system where we have real eigenvalues, the same eigenvalues, or complex eigenvalues. So because we have a linear system, we can classify this, particularly in 2D, it's pretty easy. So I assume everybody knows how to calculate an eigenvalue. However, what is interesting here to use, maybe, you can do either or, is that if we write tau here as a trace of the matrix, which is just the diagonal, and delta as the determinant, then we can write the eigenvalues in this form. So we have trace, and then delta, this is the discriminant, right, which is just tau squared minus 4 delta. So it's just solving a quadratic equation, as you know, in 2D. So that means that now we can classify our eigenvalues by using the trace and the determinant. So it's very easy to draw this in the plane, in a parameter plane, to do this. What happened? Oh. So that means we can very easily, you don't have to write down, you can look at the notes. You can easily write down all the different combinations here, right? Positive determinant everywhere here, positive trace everywhere here, and so on and so forth. But it's more revealing probably to actually put in all these phase spaces in this picture. So now coming back to your question there, right? So everywhere where we have, so this corresponds to when the discriminant is equal to 0. So under the square root, when that is equal, not positive nor negative, so that's just the boundary between complex roots and real roots. So everything, everywhere above here, we have complex roots. And here, on the left-hand side here, the trace is negative. So if you look at the trace, that means that the real part is negative. And real part negative means stability. So that means this is the only part where we can have stable solutions. So you see, and then here we have instability. So, and here we have, and this big area here, that's where we have saddle solutions, one stable and one unstable manifold. And the Hamiltonian problems we talked about live exactly on this branch here, where with zero trace. Okay. So from a lot of models, it's not obvious, but if you make the right variable change and so on, you can get a system. Okay, so notice what we had here. We have complex roots, negative eigenvalue, negative real part, positive real part, and so the transformation between a positive stable spiral and an unstable spiral is exactly that. So that's where it comes into play. So it's a transformation between this solution and this rapidly growing solution. In the middle there, you have the oscillating solution. Because in linear systems like this, and particularly here, exactly here, we fall into the Hamiltonian framework. And as I said, in the Hamiltonian framework, we only have spirals, not limit cycles, periodic orbits and saddles. But more importantly, we have an infinite number of limit cycles. So this is where sometimes things I'll get puzzled sometimes with these conservative models, because what does it mean when I say infinite solutions? So if I have the phase space here, x1, x2, so if I start with an initial condition here, then my future is determined. And I know that since I have exactly this situation, I have to have a periodic orbit. So I will have one direction here. So I'll come back to that point. If I now start with another initial condition, then I will come back to another limit. So that means locally here, I will have a family of periodic orbit where each initial condition. So I don't know, some of you might have seen this Lotka-Volterra predator-prey model. And it's exactly one of those. Depending on what initial condition you pick, you get a different periodic orbit around an equilibrium point.
Cycle, the paper that yesterday I was talking about, the growth cycle. So it gives you, it's a predator-prey dynamics between wage share and employment. So that'll give you this kind of center dynamics. If you see the transition that from, the damped oscillation and the damped but explosive oscillation, in between you have the center dynamics. If you look at the Samuelson's model again, from a damped oscillatory region to a damped explosive region, in the border you will have the center dynamics. It's a beautiful, it's a very good model to actually learn. It's a very, very simple deterministic difference equation that gives you all this nice dynamics that you'll study. So that slides that I've used yesterday, you can actually use that. This is what we teach there. So that case from damped to explosive oscillation, in between you have this center dynamics that is lying there.
So remember, this is just looking at the two-dimensional linear models. And we already, have this rich dynamics and the rich things that can happen, which I find, there are a lot of models in a lot of areas that just looks at two-dimensional linear models, but they never really take a step back and see how this is actually really, really complicated if I want to understand it properly. What happens in our math courses often is that, okay, we learn how to solve the equation and that's it. We are happy, but we never really look at what does it mean what do these things actually mean? I put it in some kind of context. So this is fine. I got an A in my differential equation class, and everything is good. I can solve the equation, but I have no idea what's going on. Right? So, yeah.
Point. Remember that if you general equilibrium model or simple demand and supply, equilibrium point, starting anywhere outside the equilibrium point for any initial condition, if you want to reach to the equilibrium point, that lambda has to be less than 0, or the ratio A, or if you think in terms of discrete system, that the ratio between the demand and supply, the slope, the absolute value has to be less than 0. If you don't have this condition, you won't reach this equilibrium. That means the exchange will not happen at all. So that's the first model that we did, demand and supply. You'll see the solution actually has this condition. You need to have, it's a discrete system, so the ratio between slope of demand curve and supply curve has to be less than 1 to reach, or the lambda value has to be less than 0 to reach this. Otherwise, you will not get to the equilibrium. That means exchange will not happen. Or the other case where lambda equal to lambda 2 equal to lambda 1 equal, both the roots are equal, gives you equal amplitude. Yeah, you'll be in a cycle.
Any other questions on this? So this is really the basics for all analysis of dynamical systems. To know that there are spirals, there might be centers, there are saddles, and then there are nodes. So nodes. So these are the nodes, and these are the spirals, and this is the saddle node when you have one stable and unstable solution. So those three types are really important when you go forward to understand that not all equilibrium points are the same. So because the equilibrium points are different, and you have to understand that. And then the interesting thing is when, did I say, yeah, so if you go back a little bit here. Yes, so on top of this, so now I've dealt only with equilibrium points or equilibria. So now if you're interested in periodic orbits, so periodic orbit, when I start at one point, after some time t, I come back to itself. Right? So that means we have a vector field, but we also want this to be true. Then we can have periodic orbits that also behave in the same way. We can have spirals along the periodic orbit. We can have nodes and so on. We'll come back to that later. So the same ideas follows up to other types of solutions as well. Okay? So let's say we have in 3D here. I'll see if I can draw a nice picture. Oh, I get hurting this here. So if you have, let's see, if you have in 3D, we have a, assume that we have a trajectory in 3D that belongs to a periodic orbit. Okay? And then you could have a spiral around that periodic orbit. So it's stable in that sense. So it's spiraling into that. So you have one direction that is the periodic orbit, and then you have two directions that corresponds to the spiral. Oh, something I forgot to say here. So we have a two-dimensional space in these 2D problems, right? So it's spanned by two eigenvectors. Sometimes we have degenerate cases. Let's ignore those for now. Or we have spirals. So there we don't have any specified directions of the manifolds, but instead we say that this has a two-dimensional space. So it's a two-dimensional manifold. So we either have two one-dimensional manifolds that we can span, or we have one two-dimensional manifold. In this case, it's the whole space, right? X1 and X2. So if you now add another direction, so we have three variables. That means we can have either three real roots or one real root or two complex conjugates. You can see, so that means we can have, one stable or unstable direction and one spiraling direction, or three directions coming together. And then every time you add another dimension, you can then have spiral-spiral, or 4 no directions, and so on. So the dimensionality makes it very complicated. So if you have 6 dimensions, you have spiraling in 3 different directions. So then, of course, it becomes hard to visualize. I'll come back to at least 2 spiraling directions in a minute here, maybe before or after break. Okay, any questions on the phase space? Because I think it's, even if you haven't done all the mathematics here, I think it's important to just have this in your head, yeah? Yeah. Which one? This guy. There, no. Which? Oh, the limit cycle. This one. Yeah. Which, if you have this guy, oh, for a fixed point, for a discrete model. That's discrete. So that means if you have a discrete model, then we have some fixed point, and that's it, right? So to reach that, we might, we might go through some discrete paths. But remember, it also typically, if you have a linear model like here, it reaches 0 in this case exponentially. So it takes quite a lot of iterations. So you never really reach. It's a limit. It's a limit of this case. So, but you can still have manifolds. So that if you have 2 stable manifolds, you can have either that you live on this and then move back closer and closer. If you have if your A here is positive, if A is negative, then you jump back and forward on that manifold. Or if you're outside, you sort of do exactly the same thing as for the linear case. So there is an analogy between the discrete and continuous cases there. Yes. Yeah.
How do you actually draw the phase space?
What do you mean?
The vector direction. How do you get?
Oh yeah. So first I find the equilibrium point. Okay. In this case, we said it's 0, 0. So it's the origin. Second, I find the eigenvalues. Third, I find the corresponding eigenvectors, and then I just draw those going through the equilibrium point or the origin in this case. And then I know then I know that it has to either leave that or go towards that. Eigenvalue. So negative real eigenvalue is it's attracting, and otherwise it's repelling. Oh, exactly. Oh, then, but if you want exact, then you have to solve the differential equation.
No, from the first Jacobian, because Jacobian gives me some indication of.
Oh, but I haven't dealt with Jacobians. But Jacobian is essentially the A. Yeah, it's essentially A. I'll come back to the linearization issue between nonlinear and linear when I get there. Okay. Okay, so if you have any more questions on this, I'll come back later and we can. So we have that went out, so about 10 minutes. So what's the next topic? Oh yeah, so maybe it's a good 10 minutes on nonlinearity, so then I can start there again. Okay, so this, I've updated the noter. So this is just a page from, I guess it was the big dynamical systems book in the 80s. Guggenhammer and Holmes, quite famous. So in the beginning of that page, the 80s, so this is the number of variables in our model, and this is everything that can happen in linear, and here we have the nonlinear world. Okay, so this was in the 80s. So we have been looking at growth and decay of equilibrium yesterday and today, exponential growth, and then you have radioactive decay. They sort of have the same kind of things. And then in 2D, oscillations, which we have looked at here. So typically simple mass, the pendulum motion and things like that can be explained if I get some picture. Oh, here we go. Then as we go up linearly, a lot of engineering structures are modeled linearly because you can get easy it's quite easy to solve, and locally you can get some stuff. Then we get up to collective phenomena, networks. We've been looking at networks already a little bit. So collective phenomena, n is equal to broad. Solid state physics, molecular dynamics, so statistical physics and things like that, often used in your models. And then from there we can then go on to continuum and start looking at waves and things like that, solitons and things like that, fluids and things, and heat equations and everything like that you've probably seen. Okay, so that is what can happen. So we have only been playing down here before. So now, and this is for ordinary differential equations. So now we can have, so you see Guckener and Holmes are using fixed points, while I'll use equilibrium points, doesn't matter. In one dimension, we can have bifurcations. We will be looking at those cases. We can have overdamped systems that you already mentioned before, or we can have relaxation oscillations like this. So both things can happen. Logistic equation, we saw, no, we didn't see it yesterday. I'll show it later. Then we go up, pendulum, limit cycles we have seen, predator-prey cycles we have spoken about. And then when we get to 3D, then that's when we can also start having chaos and things like that. So the simplest possible case is the pendulum. You have angle and angular velocity, and then if you force it with some periodic forcing, for instance, somehow, then you have three variables that you're sort of playing around with. That could give the three-body problem. It's a famous problem, with astrophysics and so on, to see how, which comes through iterated maps, fractals, Mandelbrot set, probably everybody have seen at some stage. And you see, and this is where things really that you can do easily ends. Right? After that, at least back then, a lot of this was in the frontier of research, and I would say a lot of it is still in the frontier of research. You see, economics is here. Yeah? So, because it's a big system, right? And it's very hard problem because there's so many unknowns and so many variables. Neural networks, big topic at the moment. Lots of people working on that. Heart cell synchronization, really a lot of good work on that lately. How to synchronize your heart, so you keep living forever, but a long time. And then, of course, then we continuum in 2D, continuum mechanics, very complicated, nonlinear continuum mechanics and all that. So you see, in dynamical systems, you don't have to go far before things become already very tricky. And that's why I like it. And we saw already in 2D, just looking at trajectories, it's not as trivial as it looks when you just see the differential equation. Okay, so maybe I have 5 minutes. We'll talk about attractors here, and then we'll go for a break. Okay, so steady state, what I mean by that is either, I mean, something you reach, after a long time, so you get closer and closer and closer, or if I happen to start on exactly the solution and I stay there. So for instance, if something appeared to be unstable, and we already talked about stability the other day, but perturbation, yesterday, if I'm close to the equilibrium point and if it's unstable, then I will leave. And if I'm on it, I will stay. So I probably left out a lot of stuff here, but equilibrium points we've already seen. So that is when the vector field is 0. Limit cycles. This is what I call a periodic orbit, but there's also limit cycle, which is maybe in time history, it looks like this. So let's say I start here, but then I stay constant for a while. So that means in the phase space, it might look like this. So if I have the limit cycle here, then if I start outside, I will approach the limit cycle from outside, or I might approach it from inside through a spiral. Then we have quasi-periodic. I've written attractors there, but it could also be an unstable quasi-periodic solution, which is you never see because they're very hard to get. So how many know what quasi-periodicity is? Any ideas? So think of, in a oscillation like this, we have one frequency, right? One frequency come back and forward. If we now introduce a second frequency in the system, then we geometrically get something that is similar to a torus. So how shall I write this? If I have, this is a torus, like a donut, yeah, a donut. So if you only have one period, that means that we are living just going back and forward around in this torus. But if I now add a second frequency, that means I'm also not only rotating around here, I'm also rotating in the actual. Think of a wheel. You know, you're actually going back and forward there. Right? So you live in this space, so you're rotating around, and it could be quite often that you don't come back to where you started. So you rotate about this torus for infinite many times without coming back. So what you do instead, you might fill the whole torus with trajectories or parts of the torus. You can have something that's called phase locking, so that you get exactly a periodic orbit on the torus, but just your attractor is still the torus, but you have a periodic orbit on the torus. So they are quite, so it's not a trivial thing to find. You can find them by simulation, but really hard to sort of try to follow them in an organized way. So lots of the time, when things look very chaotic or very strange, you could easily be on a chaotic attractor, because it might take 50 years to get back to very close to where you were at the side. It depends on how long these periods are, what can happen. And then you have chaotic and strange attractors. So that is just, so I'll talk a little bit about chaos, but this talk is not about chaos really. But everybody have seen some kind of depiction of chaos in books and things like that. So that just means that I'm coming back to almost the same position all the time, but almost. So then you can see sometimes these beautiful pictures of strange attractors, and different things like that. So as I said, so I'll also touch on that. So what happens in a strange attractor is that you have infinitely many saddles there that you get close to them all the time. That's why you get you're bounded. You're bounded by the attraction of part of it, but then repelled by some other direction. So it's a really intricate thing. People try to use that for controlling chaotic systems. So for instance, I have this chaotic attractor. I know that I will get infinitely close at some stage to one equilibrium point. It might take forever, but it might also be that if you say that I want to be at some distance away, then when I get there, then I turn on my controller, and then I can catch my trajectory, and then hopefully I can stabilize something that is oscillating widely. Then on top of this, we can then, of course, remember, this is all deterministic. Then on top of this, if you have a real system, we can then have stochastic, that you might be normally distributed or something. And then how you determine in many systems what is a stochastic Brownian motion type effect and a chaotic effect. This is, and particularly in economic models, that is very, very hard. Of course, there's no solution to that yet. You can do Fourier transforms and try to see if there are some obvious peaks, or if you get from noise, the behavior from noise. But it is tricky. It is very tricky. So that's why I think one has to at least be aware that could be two different effects for something that look irregular to appear. And then for the maps, we have the same things can happen. But so this is important. In linear systems, one equilibrium point or fixed point. In nonlinear systems, anything can happen. You can have infinitely many periodic or fixed points. So the simplest one is probably so sine function is 0 infinitely. You know, on the real axis, it's have infinite number of zeros, and you can have this kind of steady state solutions all over the place, and have, you know, interacting with each other, and so on and so forth. So I think we'll take a little break here, and then we'll come back and talk about nonlinearity. That's really what we're here for. So I hope the level is not too low and not too high. I hope it's sort of somewhere okay. Yeah.
You have any questions on this? See, all the time think of what you're doing in economics. I mean, think in terms of time. You're living in time. Your demand is in time with respect to price in time, supply in time. So it's a dynamical system that we are trying to understand. The textbook case of static, you know, forget it. It's starting point, but then that's not very useful because you want to talk about business cycles, fluctuations, even small things like budget making. They have announced when they use the budget, they have the provisional estimates, and then they come and revise it. All this creates fluctuations.
But also, if you think of equilibrium models, and because what you know, stress test the model, what you do is to perturb the model slightly. That means you have one of these equilibrium points, you perturb it slightly, but the behavior outside it could, you know, be very different. Depends on what type of equilibrium it is. You might not come back until a while, or you might straight go back. And you know, you never hear these kind of discussions. What actually happens in the neighborhood? Okay, let them have coffee. It's a level, okay, yeah. Everybody here? Maybe I'll start. So from now on, we're going to look at. So we have seen the basics with linear models, linear systems, and you can see even there, even in the 2D case, it's already becoming quite complicated. But the good thing is now we know about spirals, we know about saddles, we know about nodes. So that means that all that now carries over to nonlinear systems. And when we want to look at things in the neighborhood of equilibrium points. So as I said, so do we have any questions before I start? Yeah? Oh, you have it on there.
For n-dimensional space,
Yeah.
suppose for k lambdas follows the convergence, but for n minus k lambdas follows divergence. So the point where the convergence and divergence happen, we'll call that saddle.
Yeah, so it's a high dimensional saddle in that case. So some directions will pull you closer to the equilibrium point, and then some of them will, you know, move you away. So
order will be important.
But always the equilibrium points, we'll see that later, often comes in pairs. So you have a saddle and a node. So we'll see that in a minute here when we start talking about nonlinear systems. But in general, yes, you can think of it in that way. So typically, if you start with something that is stable, so all real parts are negative, so then typically, you know, you get one, and then another one, and then another one, or a pair as in spirals. So then they get pushed over to the other side. So you get more and more of these. So if you have n of these directions, so then one of them flips, you know, one at a time. Or you swap over from here up to the spiral, or from one spiral pair. But you can't go from a unstable node to a stable spiral, for instance. You have to cross over here, you know, if you do it continuously. But if you, of course, if you discretely change a parameter, then of course you can go anywhere. But if you continually change a parameter, then you have to sort of, continuously follow these changes. Okay, so from this slide, the important thing is that as soon as we bring in nonlinear terms, depending on what they are, we can get a lot of things happening at the same time in different parts of the space. We can have saddles, we can have nodes, we can have spirals, we can have chaotic attractors. Typically, of course, not everything happens at the same time because it depends on your system. But so the problem is, even if you're able to find equilibrium points, or maybe limit cycles by simulation or something like that, that doesn't tell you anything away from that, right? So, but always the way to do this is to first focus on the equilibrium points, because they often organize a lot of the dynamics. So you can see that if things look like this, so locally they would organize the dynamics. Something I didn't say here, something even in a linear system, which is interesting. So as soon as I start with an initial condition there, then first I will decrease, and then I will increase and go to infinity, right? However, if I just make a small change in my initial condition here, to the other side of the manifold, I will go to a completely different place. So what these manifolds also do, and I will try to draw some pictures here on the nonlinear case, they also separate the space into different parts where different initial conditions end up in the long term. So that, of course, even in the linear case, can make things very, very tricky. That you make a small change, but suddenly your solution completely changes. And you see, I have a linear system, but it's, something else happens. So it's something to bring home, because that's typically the hallmark of nonlinearity. That small changes in initial condition makes a huge change in the future. Like everybody have heard about the butterfly effect, right? That, if a butterfly, I don't know how true it is, but, it's flying in South America, then there will be a hurricane in other parts of the world, after some time, because it changed, the initial condition changed for that system. So here you can see, even in linear problem, a small initial condition can in some cases change the system. However, this is of course just in a very, if you make epsilon changes, if you are on one side, then you will always stay there, right? So while in the nonlinear system, a small change, whatever it is, will potentially, you get somewhere else. So looking again at 1D, so that tells us a lot about general structure. So of course, we can have any, so this is just to highlight some functions, right? So it doesn't mean anything. We can have polynomial, nonlinear polynomials, we can have trigonometric function, exponential, and of course you can all expand this, of course, in polynomials if you want to, and so on and so forth, right? So, so this is sort of the things that can happen, and if you look in textbooks, this is what you will see. You will see nonlinearities of this sort, okay? But something that you will not see in standard textbook is when you add discontinuities. So you will never see that in a standard textbook because things are not being proven in those systems yet, right? So mathematicians who work with these topics, of course, they want to prove theorems. And even in you want to prove theorems so that you can say, in every case, or in this specific situation, I will always get this, I will always get this. But as soon as you don't have differential, if you're not able to differentiate your vector field, or if you have jumps, then the game changes, right? Then you can't be as rigorous with your proofs as you would like to. So I will just introduce some types of systems that. So I've also made a very, very simple example from an economics, and you might that might not be correct, but it's the principle. So imagine now that we have our space. We have our space, and I call my whole space. So I have a space S. So that could be a part of the. And then somewhere I should have written it there. Somewhere I have some surface, and I will call that sigma. Okay, and that sigma is, and sigma here is just given by some function, just some, some function equal to 0 in that space. So here we have x. Okay, so then I can divide my space, at least locally, that's the idea, into two different partitions. Two, so that above that surface I'm, so when I'm in, when x is in S1, I'm here, x is in S1, I'm there, and I also have, if I get my picture back, then I have a different vector field in the different side. So that could mean that, so maybe I can do that example now, and then, so let's do this very simple example from economics. So assume that we are looking at the inflation. Right? So most countries try to keep the inflation at some rate. I think in Europe it's 2%, right? Typically, you want to keep the inflation around 2% because it's not too high and it's not too low, so the economy can sort of grow. So if the inflation moves around nicely about that point, then about that value, it's great. And I guess one of the easiest measures that that is available is to change the interest rate. If the inflation is too high, you increase the interest rate so that to cool down the economy, and vice versa if it's too low. So, of course, now we have had a very strange situation in the world, in Europe and USA, interest rates 0 or negative, right? Even though in some countries the inflation has been quite high, we have been quite lucky in Ireland to have had a very low inflation, in some, a good inflation, but in some places. But of course, so when this decision has to be made, that's this is measured all the time. So and so our system lives nicely. So I call the lower bound there I subscript star and I sub star. I forgot to put it into my picture. Oh, that's right, correct. Oh, that was someone pointed out. I didn't. It looked so symmetric and nice when I did it in the slide. That's right. Of course, it should be a great tool. That's correct. That's right. That's right. Yeah, looked odd, but I couldn't see. Anyway, yes. So we live in this nice world. We've used this big vector field that is the economy. It's huge, right? And then the inflation starts rising. So at some point, we go over some value that we said, well, if inflation starts to go this high, then we have to do something about it. But then, of course, so that means that the interest rate from one day to another changes. That, of course, changes the game in the whole economy. Right? So I've, of course, copied this thing wrong everywhere. So that means that we are moving to another part of the space. So we, in this case, actually have 3 partitions here, not exactly this. So I have something else, and the economy makes a big change. So it's a similar thing, as I said before, that the British government and the Irish government decided suddenly we're going to bail out the banks. That happened from one night to another. Then, of course, that changed the whole game of how to run the policy or how to run the country, really. So, of course, this thing, if you just look at your system, it's very hard to know when this happens or what this happens or how this changes in general. And, of course, this is, I don't know, so this is sort of a discontinuity where the vector field changes. So one way, so there are 2 ways to look at this, really. So one way is to think of so R here, I mean the interest rate. R is the interest rate. So you can see it as a parameter in your system, that you're changing a parameter in the system. But another way to look at it is to think of it, the interest rate is actually a variable in my system that I allow to change. So what I do at that point then is just to map it to some new interest rate. So that means here I have a different vector field in different parts of the space. Here I have the same vector field, but I make a jump in the interest rate instead. So the process, so the way I model this and think about this is different. Right? So here is a discontinuous jump here in the interest rate in my variables, while in this case it's just a parameter in my differential equations that changes discretely. So, and it has this, the effects are slightly different because you get a discontinuous vector field versus a discontinuous parameter space or a sort of variable space. Yeah? So that is, it's a sort of a different way to dynamically model these things. So
would still move smoothly. I mean, when the switch happens, the growth rate in X changes, but X
yeah, everything, the life must go, the show must go on, right? It's just that something changes. So the question is, of course, for an economy, these vector fields are impossible to know what they are, right? But of course, that's why we build small models to highlight some aspects of it. And then depends on how you want to introduce, in this case, the interest rate, will depend on how you actually model and how you treat your equations. So I guess it's the same thing for noise, right? If you actually add the noise to a variable or to a parameter in the system, you have to treat it in a different ways. I'm not at all an expert in that, but you can get additive noise or multiplicative noise, and you have to deal with it differently. It depends on how they come into play. So the same thing for dynamical systems. You have to think about how you want to treat this and model it. And then, of course, if you want to solve something, because a lot of this you can't solve analytically anyway, so you have to go to numerics. That requires different type of ways to think about the numerics as well. So that is one of the cases where I know my numerical tool that decides how I model it, rather than I want to model it the best way that actually gives me the best outcome for this particular model. So this is mechanics is quite an amazing field, not because it's fun or anything, but a lot of the things you can find in mechanical systems really transform into a lot of other fields. It's the same. I guess all these ideas about noise also came from physics first. Moving of grains or thinking of how heat is transferred and so on. How molecules are pushed forward. Then you bring it over to other fields and work with it. So it's an amazing how much of those really basic physical ideas transfer over to a lot of other systems. So don't worry too much about the equations or that. So the idea is the following. So assume that this is the belt here. So if I push my hand in this direction, then the friction force is trying to hold me back in the other direction. Otherwise, if I'm pulling it like this, then the friction force is in that direction. So that means that the friction force is discontinuous exactly when I'm not moving at all, right? So even that simple system causes a lot of issues. So this is the friction force. This is just an oscillator, and then V is the relative velocity. VREL is the relative velocity between the belt and the block here, and that's basically. And we have damping and so on. But it's not important. But the interesting thing, even in physics, friction is one of the hardest problems there is, because things can happen on micro scale, on macro scale, and different scales, the relationship between the two different materials. So even there is very tricky. So just to highlight how a switch can happen, I've just written 6 different types of switches. So here is the relative velocity. If it's 0, that means I'm not standing still. So you can have a set valued, so you allow the friction force to be, as long as I'm not moving, but I can still push, without moving. So that means that the friction force is actually changing even if I'm not moving. So that means I can have a set-valued friction force. So they fall then into a specific type of differential equations when you allow set-valued right-hand sides. So that's tricky. Then you can have, the dynamic and static friction is known. When I'm moving, it's a different friction than when I'm still. So it's affected by heat. And that of course can hold for any other system like an economy. That if I'm still, some other rules apply than if I'm moving or changing things. Then you can have nonlinear effect in your friction. You can also assume that you don't have this set value, that you actually simplify a little bit and assume that it is sort of piecewise linear or something like that, or piecewise continuous. So allow for continuity. And then you can also have this kind of effect. So if I'm moving in here, I might go up anywhere here and then move out. So you have a whole set here of possible transitions. So you have like you can have like hysteresis effects even in this case. So I'll come back to hysteresis. So why I'm talking about this is because of the modeling aspect, right? So if you actually want to be serious about modeling something, it's important to think about, how you think about even the simplest switch in let's say interest rates in this case, right? So, does it happen instantly, or does it happen in one day and it's implemented the next day, or how does this actually happen? So because that will affect your vector fields in different. So this effect now, if we have vector field F1 here and F2 here, so I'll come back to that in a minute, is that essentially you can have vector fields pointing towards this surface because they can be discontinuous. And so this surface here, in my hand block analogy, means I'm stuck here, right? I'm not moving here, I'm not moving here, but I'm stuck here. That corresponds to living on this surface. So, yeah. So non-smooth system, it's my research area. So this I could talk another 4.5 hours about this, but let's not do that. But more importantly, I just want to highlight that you can model things that seem very obvious in different ways. Depends on what you want to do with it. Do you want to analytically be able to find a solution? Then, of course, choose something that is easy, linear, something that you can do something with. If it's differentiable, you can do all these different things. But if you want to whack everything into a computer and then you can try different things. But of course, none of these ideas you would see in any of the packages, that do in economics, because people don't really know about it. It becomes too complicated. You have to think. That's hard. Yes. So if you just look at this, so what I said here, so we have one vector field F1 here, one vector field F2, and then in some cases you can also think about what's the vector field on this sliding surface. So what I say, if I stay there for some time, this is known as sliding, and it comes from control theory. So they're thinking about that you're sliding along this surface here. So that's the idea. Sometimes you can talk about sticking as well. So that means that the vector field for my hand being still here is just x dot is equal to 0, because nothing happens. However, I still have to keep track of what happens to the forces here, because if the force overcomes the friction force, then suddenly I have to swap to another vector field and so on. But I will leave here continuously from that surface. Even though the vector field is discontinuous, I will leave continuously because it's one derivative further up, or an integral up, right, from the derivative. Yes. Yeah, so if you have a discontinuous parameter, that will maybe, not always, but maybe lead to a discontinuous vector field. So that's the analogy. However, if your parameter is like I showed in my second case here, if you think of it as a, this case. Right? So if you think of the interest rate as some variable in your system, and then you make a change, then it's actually the variable itself that changes, but not necessarily the vector field doesn't have to change. It's just that you're moving in the same direction. So again, a simple analogy from physics is an impacting surface. So the only force is gravity. Right? So I should have brought something to bounce. What can we bounce? Doesn't matter. I'll bounce this. Right. So we have gravity. So we have x is position, v is velocity, right? And then I just look at the relative velocity between the table and this thing, which is of course just the velocity of this. So the simplest way to model this is using Newton's restitution law. So which means that at an impact you remove a little bit of the energy, right? So what it means that the relative velocity changes, from negative to positive, and then you remove a little bit of energy. So that's the simplest part. So there you can see that the right-hand side here doesn't change. I'm still in this gravitational field. It's just that the only thing that changes is just my velocity upwards. So in the same way, you can think of any system. For instance, this problem with the interest rate is that you can then have a jump in one of the variables, but you still live in the same world. So there are two slightly different effects here, and what is right or wrong, it just depends on the model, what you're looking at. Right? So it's just, but the way you treat it is different. So of course this somehow makes it a little bit easier because you don't have to mess about with different vector fields. You have one vector field and you just have to track when you hit this boundary, and then you make your change, and then you continue. So of course, numerically, there are lots of different tools and methods to deal with this, which is sort of far outside the topic of this lecture. But there is, people writing some serious, codes and proving, existence and uniqueness and all that stuff that is important if you want to have a reliable code. But sometimes you cannot. Any more questions on these? Yes, if you could use the thing.
About this situation as like this discontinuity, if we look at it like a possible point of kink in the curve, in the case of a linear, and make it a linear relationship with possibly some kinks over it and make it continuous.
So if you have a kink in the vector field, then it's this case. Yeah. Yeah. Then you swap between one vector field to another, right? So then if you have a kink. So I saw some of the posters had some kinks and stuff. Maybe it was yours. Yeah. So exactly. I was thinking about it because those pictures look like you're very similar to this, right? But just rotated 90 degrees. So those kind of problems you see in what are they called? It's very similar to models that people look at in mechanics, where the spring or the damper is not active for some time, and then it becomes active once you start pulling it. So you have these effects, right? So that would be exactly one of these, what I call Filipov system.
Yeah, but the problem is to identify that kink. I mean, you really do not know where that kink would actually be happening.
Yeah.
So, you basically revolve around maximizing certain functions, and you do a grid search and you come out with numbers and then you simulate about it.
Yeah, that's the beauty with reality. It's hard to do things. You can have a good idea, So I saw that you had some, data that you try to fit into this, just to see, can I model this behavior with a kink? And you saw straight away, it's very tricky. And also you might have hysteresis effects, that you might have another dimension behind, right? So that you can't pick up. So maybe even a one-dimensional model is too simplistic in your case. So his curve looked something like this, that he was trying to model. Something like that, right? So, and then you had a lot of dots here or something like that. But it could be that you actually have to introduce another dimension, there can be some slants and things like that. So if you just project it onto one, it might not be enough. I don't know. So the impact analogy is nice, not because you need to know mechanics, but just because it's a very simple way to think about things, because everybody drops things all the time. We understand impacts in that sense. Okay? Yes. So this is, and then again, even even when we have a quick change, like in the impact case, or so this, of course, just think of this as a very, very hard ball on a very hard surface, because otherwise, I'm not doing compliance or anything like that. However, one could then argue also for how long does this impact last for? So this is the velocity, how that changes from negative to positive, time, negative to positive. You can either just jump straight away. It shouldn't be a set there. It shouldn't be red all the way through. But you can also think that, which actually is that happens in reality, the impact takes some time. However, an interest rate change, I can't see that there's any continuity there, right? You change from 1.25 to 150. You just do it like that, put in the numbers in the computer, and then the whole economy changes. I don't know how it works. But somewhere someone has to put in a number somewhere. I don't know, do you know how it actually works? Maybe it's just a number on the wall. You have to follow that. I don't know. But it changes people's behavior, or the market's behavior. That's the most important. And it happens discontinuously. And so again, we saw how you can model this with Wiener processes and so on. And it's it's just two different approaches. Depends on what your model is. Yeah? And which is, I think there should be more exchange between those two worlds. The dynamical systems and the people working on noise and this kind of things, because I don't think they are really merged properly to know when one model is better than the other. But for instance, for option prices, as we saw yesterday, it works remarkably well, and you can get quite nice theory out of it and so on. So, who knows? So what else can we say here? Okay, then I'm just adding a little bit more difficulty. Okay, so in reality, again, we have our inflation. We reach some boundary. Of course, the state, the body who decides how to change the interest rate, of course, doesn't monitor, inflation every second. Right? It's impossible. So what of course happens is that there's a delay, from they notice now the inflation is far too high. Now, because they have the meetings just, I don't know, once a month, and then they sit around this round table and discuss, okay, we have to change the interest rate, and then they do it. So these systems, of course, also has delay in them, right? So, and this boundary also might be changing. So you have a lot of different effects. You have delay effects, you have the boundary effects, and because if the economy is in a certain way, then 3% might be okay. But if the economy is in a good shape, then 3% is not good. So that also, the boundary, it's a moving boundary problem in that sense as well. So everything changes here. So it's tricky. You can model it, but then at some stage you lose track of what happens because you can only do so much. But nevertheless, I think it's in the back of your heads, it's important to understand why something doesn't work as well as it do, because there are lots of, information in the background that we just brush under the carpet. And if you want to introduce delay here, then you can start looking at delay differential equations, which is again a big area of research, which is, I haven't done much of that at all, so I will not discuss this further, but that, to have differential equation that depends not only on what happens now, but on what happened a while ago. So that means that your initial conditions, for instance, you have a continuum every time period up to now. We need to know an initial condition for, because we are moving that boundary with us all the time, when we are sort of deciding what to go. So so then you get infinite dimensional problems somehow, and it just get more complicated. So so people, of course, are doing that, are very good at doing that. But this is, then things become very technical, and numerically it becomes very technical as well. But doable. There are lots of some decent packages working on delay differential equations now. So.
Delay case would be significantly different from, let's say, in this example. So we say that there's one way is either you hit the boundary, you change the behavior.
Yeah.
The other you pointed out is that there is a delay.
Yeah.
After that you change.
Yeah.
But you can also have a third condition which says that look, only the inflation persists above this level for a certain amount. So you cross it, but then you come down, right? Then you say, okay, I'm not going to do anything.
Correct.
Would that be a completely different
Yeah. So you will have what you're saying, if I understood it right, is so we have a target there, we have an upper limit. So you have inflation go up, but then you go down again, right? Something like that. So that means that, so hopefully, the people meeting in this room, they're looking at it. They're probably not just looking at the value. They look at second derivatives, third derivatives. They see if there is, acceleration in the inflation, and they look at all these things, right? So hopefully, if they have a meeting here, they see that inflation actually, it's not as bad. So they probably wait. So of course, even in the decision making, which is what happens here, there is a lot of more effect and delay effects and everything. So you can have. So this is really delay in the decision and the boundary. But then, of course, these guys themselves could have a delay because interest rate, things don't, typically companies and so on maybe don't change all the time. That's when they see that they're selling or buying more or less than they expected. Then, of course, stock market changes because of that. Not until you have the information. So there's, of course, lag in information in all these things as well. Okay, so started to look at stability, which is sort of the basics to actually get to the bifurcation parts. Okay. All right, so we have already looked at this this linear differential equation with the exponential solution. Okay, so I assume that x of 0 is equal to 0. So we said that the parameter here, a, in the linear case, will give us whether we have a stability or if you have instability. Okay? So the green corresponds to the equilibrium point, and if you make a small perturbation, in this case, we will exponentially go to plus or minus infinity, depends on the initial condition. So that's what we are thinking about, stability with respect to small disturbances. However, the stability is a very important area in a lot of mathematical science and control science. So there are at least 15, 20 different ways to look at stability in different spaces and different norms and so on. So I'm just briefly mentioning two here. So if that is something that interests you, you can look at stability. So asymptotic stability, that's when we go from a disturbed solution, like in this case, we disturb it slightly, and it exponentially goes back to the equilibrium solution. So that's what we call it asymptotic stability. So it asymptotically goes back to the you can have yeah. So the other one is that I'm just mentioning here is Lyapunov stability. Is when you have a solution, you perturb it, and you stay close to that solution for all times, but you never reach it. So we have already seen one of those cases today. We have seen one of those cases. Does anybody remember what case that might have been? So if you look at the center solutions, right? So we have about the equilibrium point, we have a family of periodic orbits So if I perturb it slightly here, then I will never come back to the equilibrium point again. So then I will stay, but I'll stay in an epsilon neighborhood if I perturb it an epsilon. Right? So there are, so this is still a sort of stable setup. And then of course, if you introduce noise and stuff like that, so that would mean that you probably, in this case, you would stay in the neighborhood. Also in the asymptotic case, you would go down here and you will stay. Hopefully, if the attraction is bigger than the noise, the forcing from the noise, then of course you might stay in this neighborhood. Is that clear? So now I'm going to just show the derivations for how to think about this. So we'll start with the equilibria for one-dimensional system and then do ND briefly. So there are basically three things that can happen. If we look at our vector field, we have found the equilibrium point such that the vector field is 0, evaluated at the equilibrium point. So then there are three cases. We can have the f prime, which is df dx, is less than 0, greater than 0, equal to 0. If it's less than 0, it's a stable equilibrium, and I'll show you soon why. If it's greater than 1, unstable equilibrium. If it's 0, the first derivative here is not enough to determine. We have to go to higher orders, and I'll show you what I mean by that in a second. So this is really what you should bring home from this. Right? So if you have a one-dimensional problem, you find the equilibrium point by solving this equation, then you look at the first derivative, which is a one-dimensional Jacobian, right, in this case. And then we solve. So this is, the analysis here is very straightforward. So we have our real axis here, our x. We have x equilibrium at some point. Right? So then we perturb it initially by some x. We have some epsilon at 0, some perturbation. Okay, so that means we let x be the equilibrium point plus. So we look at this point here, and that's just x of t is equal to x equilibrium point plus epsilon of 0 initially, or maybe epsilon t. So what we're interested in here to see, how does the perturbation evolve over time? Right? So if the perturbation goes to 0, that means that then I'm back at my equilibrium point. If the error term increases, then I will not come back to equilibrium. So quite straightforward. I differentiate this with respect to t. So this is just a constant, so I get d to t. The right-hand side, instead of x, I put in this Taylor expand about the equilibrium point, because epsilon is a small term here. So it's a very straightforward analysis. So I get all these terms. So we know from the premise was that we have found an equilibrium point. Right? So that means that this term is automatically 0, and these are higher order terms. So assuming that epsilon squared is much smaller than epsilon, as the standard thing you do. So we just look at the linear part. So essentially, we have linearized this problem, and what remains if we put in this guy equal to that guy, we end up with this. So this gives us now a differential equation for the error term. However, this guy is now just a scalar because we are evaluating it in the equilibrium point. So that means this is exactly the same as having epsilon, oops, wrong color. Having epsilon dot is equal to a epsilon, which is an equation we've already seen before, right? So this is f prime of x. So that means now, and this one we know the solution to, right? It's e to the power of, so the solution to this guy is x of t is epsilon of t is epsilon 0 e to the power of f prime x equilibrium. So that means that if this term is negative, error term goes to 0, positive goes to infinity or something. And if it's exactly 0, then you can see, then we have to take, if this is 0 and this is also 0, then we have to take higher order terms into account. The interesting thing here now is also bifurcations. When do you think they happen? So here we have stability, instability, and in between it's 0. So of course, the nasty stuff happens exactly when the derivative is 0, right? Because that's when you allow for more things to swap, right? That's when the qualitative behavior of your solution changes. And that's exactly in the linear case when A was negative and A positive. So that's a sort of, but in nonlinear equations, more things can happen. So this is good. So that means now that, you know, we only have to really to find stability. We only have to look at the derivatives here. Okay? If we can find them, we might be able to estimate them if you have data or something. You might be able to get hold of them. I know in biology people do a lot of these things. Try to actually find Jacobians in order to find periodic orbits and find equilibrium points, just to get some kind of idea about it. So in ND, it's exactly the same. However, the only thing that changes, I'm not doing all the, is that, so now epsilon here is a vector with all the error terms in all the different directions. Epsilon 1, epsilon 2, epsilon 3. This is a x and epsilon is an Rn. We assume that all the separate terms are small. And then this is just the Jacobian. So now we have the epsilon t Jacobian evaluated at that, which is exactly as our term A in our linear case before. And then we can look at the eigenvalues of this, and then we get all that plethora of possible solutions, nodes, spirals, centers, and so on. Okay? So that means we only have to look at the Jacobian, which is the partial derivative, evaluated at the equilibrium point. So you see the equilibrium point here is essential, if you can find the equilibrium point. Yeah, so now we can, if you have this equation here, we can now compare this to everything we had before. So we can see that the error might be spiraling back into it. It might go along as a node, or it might be a saddle or something like that. So everything can happen here. Okay, and similarly here, when do you think bifurcations or strange things happens for this model? So when you remember when you went from stability to instability, that's when the real part of some eigenvalues, or at least one eigenvalue goes from negative to positive, or vice versa. So that's where interesting thing happens. So in 1D is the value of the actual derivative. Here is the eigenvalues. That makes sense. Because now we can use that whole linear machinery that we spoke about in the first hour in order to get hold of the stability. But remember, this is now, what we do here is something called linearization, right? So we just look at a small neighborhood about an equilibrium point. What happens outside in a nonlinear system, who knows? It is a case by case. Sometimes the behavior holds for large chunks of the space. Sometimes it's very, very small. Depends on the model. Sometimes things happen very rapidly, sometimes not. So again, there's so many different possibilities here. So, but remember, this is just local behavior that the linearization can do. Okay? But nevertheless, it's pretty powerful. And for maps, I also put in the map case here. So for maps, it's the same. Now we have a discrete version of the epsilon, and we end up with this discrete equation and solution. So you see that if the absolute value of all eigenvalues of this is, I'm not doing all the analysis there, but you can sort of reformulate the problem slightly. So what it essentially means, if all eigenvalues are less than 1 in magnitude, so you're basically in the unit circle in a complex plane with your eigenvalues, then the discrete model is stable. Otherwise, it's unstable. So is this any questions on this? Because this is everything there is to, not everything, but this is the basics to stability, really. What do you mean by that? Yeah. Yeah, it sounds, I don't know that stuff, but it sounds very likely because, you know, the things don't move very quickly in those cases. So, at 1, yeah. When you're, so if you have, so you have different possibilities here, right? So you have the real of lambda and imaginary of lambda, and here you have 1, 1, also minus I, minus 1, and minus I, like that, right? So if you move along the real axis, then you will have certain type of bifurcations. We'll see those in a minute. And if you move up as a complex conjugate pair, then you will have other types of bifurcations. Any other questions at this stage? No? Okay. So I just decided, so because periodic orbits and limit cycles it's a very fundamental thing in dynamical systems theory. Just wanted to mention the idea behind how to deal with that. So remember we introduced this Poincare surface, right? So we're coming back to ourselves. So what we can do is to use this idea that we introduce a surface, but instead of, and we're interested in stability of a limit cycle. And so imagine we have, I don't know, we have some space here, okay? So we have a limit cycle. We're coming back to that surface at some stage, right? So what we need to do, and this most likely has to happen numerically. So you want your initial condition be the same condition as when you come back after some time t, right? So here we have x of t0, but at the same point we also have x of t plus t. So if you think of the case in an equilibrium point, okay, so we have an equilibrium point here. So what the linearization is essentially doing is to look at the small neighborhood to see if you're inside that, then I will come back into the equilibrium point. So what we want to do for the limit cycle, we want to do the same thing. So we want to see how a small initial condition here spreads, you know, along when we come back here. And if that region is smaller when we come back, then this will shrink and become smaller and smaller, you know, when we simulate, right? So that means you have contraction in the neighborhood. And there's a very simple way to calculate that. Is that instead to having a differential equation, we now have a matrix differential equation. So we just have to simulate the Jacobian. What happens to the Jacobian? Because the Jacobian tells you what happens with perturbations in different directions, right? So now if we start with a identity matrix, it means that we have no perturbations, and then we multiply Jacobian with that and solve what happens along this tube, and then you can get the eigenvalues for the solution when you know that you have a limit cycle. So in practice, what you do, three things in practice when you do this numerically. You put in I don't know, do you do a lot of numerical methods in India? So do you know what a boundary value problem is? Yeah, so this is essentially a boundary value problem, right? We have the initial and the end state. So I'm thinking of a way, something called shooting. That's the easiest. So you start, and then you see where you land when you come back to the surface. So then what you do then is that you get hold of this matrix, which is an approximation of the flow Jacobian, if I call it that way. And then I use Newton-Raphson's or something, to update my guess, and then I get closer and closer to the limit cycle, or at least on the surface, but it is essentially a limit cycle. And that means I get two things in one go. I get the limit cycle, and I also get the Jacobian. And then I look at eigenvalues. And because I'm thinking and for limit cycle, you have to think about this as a map, right, back to the surface to itself. So then you can look at eigenvalues in this complex plane. So I'm not expecting you to understand and go through all this, but it's a nice theory. And particularly, you can look at this for linear problems as well, and so on. But at least I just wanted you to know that it's possible to find stability of also limit cycles, not only equilibrium points. A little bit trickier, but the same ideas allow. But it's just that you're looking at the whole trajectory at the same time, rather than the equilibrium. Then quasi-periodic, tora and stuff, much trickier, much trickier. Then you can look at Lyapunov exponents and stuff like that, but I'm not. Okay, so these are known as first variational equations, if you want to look them up, if you're interested. So that could be of interest. Okay, so now we have sort of dealt with the stability. So for the next half an hour now, and then beginning of next hour as well, we'll start looking at what we're really here for, looking at changes in the systems. Okay? Unfortunately, I think it's important to have this background to understand where all this comes from, because otherwise it's just graphs and doesn't mean anything. Now at least you know what stability means, you know what equilibria means, and what limit cycles and so mean. So that's the message. As Raghav said, think of this in the terms of the problems you are working on. That's why I'm not putting in a lot of just mathematical nice examples, because I want you to just think of it in general terms, as what can happen in my system, and what is it possible to even model those systems, and what would be changes, and so on. Okay. Oh, I should have. This is an interest. So yesterday, Vishu was talking about this. Maybe I don't know how to introduce this to make it really easy. So the basin of attraction is basically, if you look in your space, all those initial conditions that will eventually lead to a specific attractor. So if you have many attractors, so I'll show some examples just to show you how complicated they can be later. But just think of them. So if you have a lot of different attractors, then of course your space is divided into different parts where different initial conditions go to different things. And also what separates them are manifolds. Okay? So if you remember, so when we looked at if you remember, in the linear case, we use the manifolds as the eigenvectors of the matrix, right? So assume we had two linear cases. So what you can show here is a powerful theorem to show that locally the manifolds given by the Jacobian and its linear counterpart are equivalent. So locally you have the same behavior in the nonlinear system and in the linear system, and that is very important. What happens to the manifolds away from this locality could be anything. They could even interact in the worst cases. So that, but that, I'm not dealing with that here at all. So if you remember, so if you have, let's say this, or let's say we have a node like this. So that means that now we have stable manifolds that can live all around the space, do a lot of weird things. You have unstable manifold, so this is wrong direction. And also, these manifolds now separate where solutions can go to. So do you remember, I said if I'm one side, I will go somewhere else, and if I'm this side, I might go somewhere else. So these manifolds will now separate what can happen to initial condition. So that's pretty tricky. So if you in the one-dimensional case we saw yesterday with a bowl, so we had the bowl initially, right? When we have the ball and we fall back into the lowest energy state, if you want it for a ball. So that means that here everything is a domain of attraction. If you have something like this. However, if it instead looks like this, we'll come back to this later. Okay? That means that where is the domain of attraction now? So this is a stable state. This is an unstable state. So where is the domain of attraction here now? So the domain of attraction is everything from here all the way to minus infinity, say, if this is the real axis. So what's the domain of attraction for the unstable? So only that point is the and then minus infinity here, or plus infinity, sorry, is the domain of attraction for everything to the right-hand side here. I will use that analogy when I talk about the bifurcation. So, of course, these things can be very complicated, right? So, and in 1D this is, but then in 2D, then you can think of these being a surface in 2D, you know, being very complicated. How can I get from one place to another? And they can sort of start swirling inside each other and stuff like that. So this is, basis of attractions is a whole topic on its own, which is very interesting. But I don't want to spend too much time on it, more than saying that when you have a nonlinear system, it's not clear where you end up. Then, okay, and if you have different attractors, in 1D like this, it's clear, right? Yeah. Yeah, I will. You know, I'll keep all the examples till the end. So the afternoon session will be a bit more lighter. So I will show a lot of bizarre things. So if you keep there, so I think we'll do that. So then it's nicer. Yeah. Yeah. There another no. Okay. Yeah. So that's essentially what it is. So maybe. Yeah. Let's leave it at that for now. Oh, actually, I did have an example. I must have changed my mind. Okay, let's look at this simple case. So finding the equilibrium points here are pretty easy. So F. So we have. Okay. So if we want x dot to be equal to 0, that tells us that x is equal to plus minus 1. Okay? Very straightforward. So that means we can plot that in our plane here. Okay. So if I do it this way, so then you can see. So if I now introduce another axis, I put in f of x here. Okay. So then that looks like this, right? So we have 1. So this is f of x. So now we can easily see here that here f of x is negative. That means here I have to move in that direction. here x is positive, so I have to move in this direction. And here x is negative, so I move in that direction. So that immediately gives me that is a stable point, and that is an unstable point, without even doing the analysis that we already know we can do, right? So that also means that the basin for 1 here is from -1 to plus infinity. The basin for -1 is just that point, and the basin for minus infinity is everything left of -1. So I'm going to use this notation as well. If I have an unstable point, I will put an open circle, and if I have a stable point, I will put a filled out in circle. I don't know what I've, oh yeah. So we can also do the analysis here. So if I differentiate f, then I get -2x. Right? And if I then put in those numbers, we see that -1 is positive, evaluated at the equilibrium point, which should mean unstable solution, which is exactly is. And if I evaluate at another point, the derivative, it's negative, should be stable, which it is. Right? So in low-dimensional problems, you have a lot of different tools. You can look at it from sort of graphically or geometrically, if you wish. Or you can, if you like analysis, you can do the analysis. It's completely equivalent. However, at least I can very easily, in my head, see when I do things like that, what's actually going on. Okay? So with bifurcations, what happens now is that instead of having a 1 here, we can have a parameter there. And then that means that when we move this closer to 1, the equilibrium point gets closer and closer up to a point when it's exactly there, and then they disappear. So that is a saddle node bifurcation. I'll come back to that just in a few minutes. So that is when bifurcation geometrically do occur. Two equilibrium points coming together, destroying each other, but what mathematically happens is that this curve is just moving downwards, so you can't have any solutions. So we'll see here in a minute. Okay, so now for bifurcation. So now assume now that we have some parameter, which is similar to what I put in there. Okay, so now we assume that this differential equation has an equilibrium at that for some a, okay? And we still want the equilibrium condition to hold, okay? So now we can get, and this is of course what everybody here is interested in. So first of all, is the equilibrium point stable or unstable? And for what values of a is it stable and unstable? And how is it, how's the stability affected as a is varied? Okay. So I just put in a few of these references here, but there are millions of books on bifurcations, right? But there are some good ones, the classic ones. Guggenheimer Holmes, I always said, is quite nice to read. Strogatz, which I didn't put in, I should probably put it into my notes, which is a basic book to get into nonlinear dynamics. Wiggins, I've looked at lately, it's an interesting book. Kuznetsov, who I've actually written a paper with, he has a good book on bifurcation analysis. I think it's a new version really recently as well, so fix some errors. So this is the questions we are really after. Okay, so there are a lot of different ways in which the qualitative behavior can change. So what I mean is, if my equilibrium point, limit cycle or something is stable and I vary a parameter, so what I mean when I say qualitatively is that it either changes stability or it disappears or does something else. So it vanishes to exist. Typo there. So I'm going to talk about 3 of the basic ones here. And they also lead to catastrophes or rapid changes in some sense. So we have saddle node or flip bifurcation. So saddle node or flip, they used both of those words. Transcritial bifurcations and pitchfork bifurcations. So I'll start with those. And that's basically only for the 1D problems. So this is really, so the sudden node bifurcation we already saw here. So I'm going to remove some of this stuff and then draw this. So the sudden node bifurcation is, so when you vary a parameter on one side, so this is what I call the bifurcation point. Exactly that point. Okay? So that's some A star here, and then I should also put in some X star there. Right? So all these correspond to equilibrium points. Right? So remember this picture now I had. So assume that I do something like this. I have X, I put F over X and A here. Okay. So let's see. So we get the right solution. Yeah, that should be exactly what we had before. So at these points, we have F of X is equal to 0. That's when we have equilibrium points, right? So, and the height here is my A, right? So I have an unstable solution there, a stable solution there. So when I change A, then of course these points move together, and at some stage they completely come together here, and then so actually then I have something called, exactly at that point I have a semi-stable point. So I will go to that point but leave there, and then when I get below this, then there's no solution, and that's exactly what it is here. We have two solutions coming together, and geometrically think about it, it's like this. So another way to look at the transitions that I often use are these kind of pictures. So I have so I have X here, unstable solution, stable solution. Oh, maybe I have arrow, arrow, arrow like that. Okay, maybe you can't see. Then they come together at the bifurcation point. So I have a half stable. So I have arrows coming like that and arrows coming like that. And then in the last picture, I only have arrows like this. Right? So here you can also see I put in arrows like this, which is very helpful. So that means for a given value A, if I start with an initial condition there, I will fall down to that. Right? So for a given parameter, I'll just fall down there, and maybe I did it the wrong. Yeah, so this is slightly different than I had. Yeah, there's just nothing, but I must have done some mistake here. I don't know. Oh, I actually swapped it. So the case I've been doing, the case that you see here is actually this case. So I have a stable solution there, and an unstable solution there. And then they come together here. So that case would look like stable, unstable. So the way I saw that is that to the right-hand side of this, all dynamics should just go to plus infinity. And so that means that to the left here, the arrow is going to plus infinity. To the right of all this is going to plus infinity. So when they come together, it has to be consistency everywhere, right? So you can see below here, it's going to plus infinity. Above is going to plus infinity. So that is, so of course, now you can think, assume that we have an equilibrium point. We allow our parameter A is varying in the system. We are plotting along nicely here. Suddenly we reach to that point. Everything disappears and we go somewhere else. Right? Another thing, if you remember, so the bifurcation point, as I already said, happens exactly when the derivative is equal to 0 with respect to the variable. Right? So that means that when we get closer and closer to here, it goes to close to 0. So that means that the dynamics there is very, very slow. In the neighborhood here, the dynamics is very slow because the vector fields is very small. So that is sometimes, if you look at the literature, that can be referred to as critical slowing down, because locally things are really, you're part of the dynamics locally is not as quick as it would be elsewhere. So that is one of the bifurcations. The second one is the transcritical one. So here, what happens is that you have two branches of equilibrium points coming together, and they swap stability when they go through each other. Okay? So what would that picture look like in the bifurcation world? So everybody knows to install R. Good. So what would that look like? We have this picture. So we have, that would look like this, something like this. Here we would have a stable and unstable. Okay, so f of x is positive here, so we are moving in that direction. Here f of x is negative, so we have to move the negative direction and so on. And then what happens, so then those two guys come together. So what will happen with the graph then? What will happen is that they will come together in this way. So one point is together. And then finally, then it will go below again and do something like this. And then then that becomes unstable and unstable. So maybe I'll draw those three cases here. So we have this case, we have this case, and then this case. So here we have stable, unstable, yes. Something like this. You see, the point we had here changes stability, and the guy that is moving from left to right. So this is how it becomes stable. Okay. But in a picture like this, it's more easy to actually see what happens. So we have, and that is quite common behavior, that two solutions come together and they swap stability in that way. So would this case be as dangerous as this case? What do you think? Any ideas? Well, so let's see what happens. So we are close to this equilibrium point. The parameter is changing. Our system is moving on nicely. We get to the bifurcation point, but instead we just have a nice smooth trip up here, and there's no rapid changes or anything like that. We just move to this other branch. However, it's all good. The problem is if we have a perturbation that takes us down there, because then we will go. So if you have a bit of noise here, and you're plodding along here, then you end up here. Then your domain is minus infinity, and you're thrown away. But if you're above, then it's fine. So it's very sensitive in those positions what can happen. So that is interesting. And the third one is the pitchfork. And that typically only happens in systems where you have clear symmetries. So because here, so what you have here is you have one stable solution and turns unstable, and at that point, two stable solutions are born. And they are known as supercritical. It's a supercritical pitchfork bifurcation. And then you have the other case, which is a subcritical. you start with a stable equilibrium point. At the same time, you have two unstable equilibrium points surrounding you. And they come together at that point, and then the stable equilibrium point turns unstable and looks like that. So what would that look like in a similar picture? So now we have something with three solutions, right? At some stage, and one solution at some stage. So if you start, let's start with the left case. So we have a stable solution. So that looks like something like this. So we have x and f of x. So that's, x and a. So that looks like that first. So then we increase a. So then we have one stable here. Then we increase a. Then we get something like this. Okay. And then when I move further, maybe. And then when I move further, it will look like this. And then. So I will have. So again, it's a geometrical thing there. So then this turns unstable. This turns stable. Stable. So we have that. So you can see a lot of this is about functions and geometry, really, but the effects are important. Okay, so of these two guys, which one seems dangerous and which one seems quite nice? What? And that's right, for the same reasons as before. So here we have. So even if you have noise here, we plot along here, change the parameter, and then we have start following one of these guys. So we have a nice smooth transition, and you can sort of react. This one is brutal, because here we are plotting along here, and then we can go to either plus or minus infinity. So it's even more, it's impossible to know where we end up afterwards. So, and you can see the only thing you need here, we'll see that last bit here. The only thing you need here is there's some kind of cubic equation, that your underlying dynamics has something that is cubic, which is not that uncommon. Something linear times something that is a square. Those kind of effects. It's quite. That's not very unusual to have something like this. Yeah, that's right. So you can flip this in every direction, right? So you can get all the mirror images of this. Yeah. So if I do it that way, like that, yeah. Oh, you can do both flips. Yeah. So you just have to do the. Oh yeah. So I think if you flip it like that, you will get the right case, right? And if you flip it like this, you will get because it's a rotational symmetry here. So it's yeah. So yeah. So that is, so this is the magic. This is the magical thing about bifurcation theory. It's not that magical, really. It's just you have to sort of just think a little bit about it. Yeah? And we are still just working in 1D here. So what I did here in the notes here, I left you some theorems that you can just look at. So I'm just giving an idea what it is. So for bifurcation, so if you actually want to find a bifurcation point, so this is for the saddle node, then all this has to hold. Okay? So this gives us the equilibrium point. This gives us that the derivative is 0. And then this gives that they don't fold in on themselves and so on. So it's a geometrical issue. Okay? So the signs of these guys tells us how they're flipped in the space, if they are from left to right, right to left, and so on. So they are, for simple functions, they're easy to change. Okay, so all this has to satisfy. So you can imagine if you build a computer code, then you just have to put in all these functions and solve them in order to bifurcation points and so on. So here is for the transcritical one. So here you can see similar conditions. Some has become 0, and also this term has to be non-zero. So it's essentially, so what does it mean? It says something about minima and maxima, right, in saddle situation. And then, so this is the transcritical. And then we have, for the pitchfork, even more conditions. So you have to have the birth of the quadratic equation, for the two solutions, and then you have to have the bifurcation and so on. And then there are these two other conditions. So whether the system is supercritical or subcritical, as we saw, is very important, because that tells us whether we have a nice kind of situation or not so nice situation. So to be able to check whether it's a super or sub, it's quite good in a simple way. However, if you have a very complicated system, to find the third, this corresponding to the third derivative for a Rn system, it's a little bit tricky. In 1D, it's easy, right? But what, that's some kind of tensor kind of thing, which is, but quite often, so this is another important thing. Quite often, you can, so if you have a big system, there are only some parts of the system that is part of the bifurcation, right? So if you can use some system reducing techniques to bring it down to this level, just to look at this local behavior and then bring it back out, and then because there's always only either 1 or 2 eigenvalues involved in all this, right? So there's only a sub part of the system where things happen, even if it will affect the dynamics of the whole system. But of course, if you're able to localize where this happens, then you can do this kind of analysis locally and then bring it back up. Okay? Because some variables might not change at all, when A is varied, and some will change a lot. So where are we now? So we have 5 minutes. Maybe I can talk about this bifurcation as well. So that was for one-dimensional problems. So now we have the situation where we are moving to, we have an equilibrium point, and suddenly we get a limit cycle. So, and that is through something called the Andronov-Hopf bifurcation. And if we remember this picture we had before, maybe I can draw it over here. We have the trace, we have the determinant, we have the, I call this delta is equal to 0, which is the discriminant is equal to 0. So here we had stable spirals. Okay, here we have unstable spirals. So in the linear case now, so in the linear case, we had center solutions on this, right? Exactly here. Right? But for nonlinear system, we cannot immediately say that we're going to have centers. And the bifurcations that the Andronov-Hopf bifurcations happens exactly when we vary some parameter in the system so that we cross this transversally. So we might have a stable equilibrium point here, and then on the other side, that changes stability to an unstable spiral, and then we might have a birth of a limit cycle as well. So that's a sort of very different behavior as before. So you can sort of, in some sense, I don't know how true this is, in some sense it's a two-dimensional version of the pitchfork bifurcation. So you have one solution turning unstable, and at the same time you have a birth of a completely new branch of something. In this case, it's not two solutions, but it's a limit cycle instead. Okay? So So this is, I don't know if you can see properly. So we have sub and supercritical versions here as well. So we have paths spiral into the equilibrium point like this, in here. Then when we vary the parameter to the right-hand side here, for each parameter we have some limit here. So it's a stable, and then we have stable limit cycles here. So that's why it's a supercritical. So remember, supercritical means stable turns unstable, unstable, and then we have a stable branch on the unstable side. So that's a super. And the sub is unstable, stable, and then we have unstable like this. So in the subcritical one, so here we have unstable ones spiraling up to infinity. Here we are spiraling into the equilibrium point, and between those we have a unstable limit cycle. So if you look at that in phase space, that would look something like this. So you have an equilibrium point there, then we have solution spiraling into the solution. We have a unstable limit cycle here, and outside here we are spiraling out. That would be the case where we are here. So here again we can clearly see which one is the dangerous one and which one is the nice one. Here we're following an equilibrium, and then when we get to the other side, we start getting small oscillations. So the example I usually teach my students is, as an academic, you tend to travel a lot. And you go to airports and you sit there and do nothing. It's quite boring. But then you can sit and watch people, and then you can see they have problems with Hopf bifurcation. So they typically they're running with a trolley, nice and stable. They'll start walking faster, and then the trolley starts to wobble really badly, and then it might turn over. The map. Yeah, so they walk around with a trolley, and then they start walking faster, and then the trolley starts to wobble, and it might even turn. So I know I had this happen to me recently, and I actually started to laugh because Hopf bifurcation. So a bit weird. Yeah. A more severe one is wobble for motorbikes. You have a nice speed, you speed up suddenly, and then suddenly your front wheels start to oscillate. And that is much worse than a trolley case in the airport. So even though I said it's not harmful, depends on the situation. If you're driving a motorbike, then it's not very nice when it's oscillating. However, I guess it's better than this, because then you would go out in the bush and do somewhere. So maybe this is a good time to finish with subcritical with Hopf. I just did the mirror images here. So what shall we start with next? Maybe I'll do this. Similarly, there is a theorem for this as well. So I just put it up there so that you can see. You check that so this is for 2D. You check the Jacobian. You look at the eigenvalues as they vary with some parameter A. Then you can make sure that it crosses this line transversely, so it doesn't turn back exactly at the boundary, because then you won't have a Hopf bifurcation. And then you can, then a lot of different cases can happen, spiraling in and out. So that's good. So I'll start with normal forms, which are that's the sort of beginning of the catastrophes that we're going to look at a little bit later, and then tomorrow Vishu will talk about catastrophes more, and then I'll show some examples till then. So yeah, that's about it. If you don't have any obvious questions now. Now, an onslaught of dynamics. Yeah? I hope you're not spiraling out of control. I guess we'll have lunch, and I'll see you again in an hour and a half. Oh no, 1:15. Oh, sorry. Yeah, otherwise it would be a short break. Yeah, 2:15. Yeah.
Okay, we'll start. We'll start with second set of lectures by Petri.
Third. So, any questions so far, or is everything crystal clear? There can't be any confusion about anything so far. Huh?
You may want to just formally define mathematically what constitutes a bifurcation.
Yeah, so
It's not clear that it's not the change in the solution, but the behavior of.
so bifurcation is, so mathematically there are two things that happen. So one thing is we need a equilibrium point or we need a limit cycle. And secondly, we want the Jacobian or the first derivative to go to 0 at that point. So that means that the stability at that point changes from positive to negative. Then depending on what the system looked like, we can, as we've seen before, we can get different behaviors. So we can have, so in the first case here, so it depends on what the equation looked like. So I'll come back to that in a minute. So you can either have two solutions coming together, disappearing. So that's the bifurcation point. Secondly, we can have two solutions coming together, both of them changing stability and living on the other side. Or we can have situations where we have one solution on one side and three solutions on the other side, and where one of the solutions change stability. And the fourth case was the Hopf, which again, it's a similar situation, but here we have one solution on one side, it changes stability, and we have a family of periodic orbits on the other side. So in all those cases is that at that point, either the real part, so in all cases, the real part of one or two eigenvalues, depends on what situation it is, goes from negative to positive or vice versa. So that is a sort of simple sort of explanation. Then, depending on what case it is, you can look at all these conditions and so on. So what people have done, of course, and this is important, if you have a model, you think that it has bifurcations. If you can reduce the dimensionality or find what part of the system is of importance, then you can, changing variables and normalizing and so on, you can hone all this down to what is known as normal forms for these equations. So what I plotted there is exactly solutions to the right-hand sides here. Right? So saddle node, a plus or minus x squared, which is exactly what I showed on the board over there, right? That's exactly the square solution. So setting x dot equal to 0 gives us, so if x is equal to, so what do we have? A plus minus x squared. So x dot equal to 0 gives that x is equal to plus minus, let's see, try to do this right. Something like this. So in some cases, depends on A, you will have solutions, and in some cases you won't have real solutions, right? And where there is no real solutions, that is obviously to the right-hand side here. Right? So it's only solutions for in one side of this bifurcation point. Oh, that is a typo, yeah. x1, x2, sorry. So what you can see here, so you can really reduce the local behavior to three very simple equations here. So we have saddle node, we have the transcritical and the pitchfork. So we have up to order 3 there, and then for the Hopf bifurcation, we needed to have a 2D system in order to be able to get periodic orbits, because on a line, you can't have periodic orbits on the line.
So what you're saying is, if I have a nonlinear thing, but near the equilibrium, if I
yeah.
then that would tell me.
Yes, yeah. So there are also, when you do that, you can see that some terms will fall off, right? So I didn't want to introduce all that analysis here, but essentially, yes. So you change variables, simplify things as much as possible, tailor, expand, and if you have those 2 terms in the leading 2 terms, then you have. So that really, so when you build a model of some sort, then you can all sometimes see whether you will have quadratic or cubic terms, or it's indeed linear. Depends on how you set up your problem, and that sort of gives the whole story. And also, so what I plotted there was exactly the solution. I chose 1 plus or minus there for one of the solutions to show that. And all these 3 cases correspond exactly to, we have the cubic there, we have the quadratic there, we have the quadratic there. So they move in different ways, depends on which of these different equations there are. Okay? Normal forms are also used in other areas of dynamical system, but here is. In these cases, A equal to 0 is where this transition. Exactly. So in all these cases, x equal to 0, a equal to 0 is the bifurcation point. Right? So that's exactly the way I've plotted here. Right? So that corresponds to 0 and 0, exactly that point. So everything has been, whatever you are in the plane, you shifted back to that point, so that you get the simplest possible the form, right? So otherwise, you cannot. If you don't do that, you will have equations that look like this. Maybe you'll have x dot is equal to. So let's say we choose the second one. Maybe something like a minus a bar, some constant, and then you have x minus x hat plus minus x minus x. So that means you can shift, if you shift the bifurcation point to somewhere else in space. But it's exactly it's exactly the same idea. Just change of variables in that case. Yes?
So A actually corresponds, A is equal to 0 corresponds to the Jacobian being.
Exactly that. Exactly that. Exactly that. Yeah.
Is there an order you put on equations to identify what's the simplest possible equation?
What's that?
Is there an order that you put on equations?
If there is a what?
You define an order on the equations,
yeah.
Figure out what is the normal form. Like, is it possible to which is the simplest possible form? Because it's a simple, you need to have a definition of complexity, right? On equations.
Yeah, so tell the question again.
So when you say simplest possible form, you need to have like a measure of complexity of the equation, right?
Yeah.
And so that would require some kind of an order on equation. So is there a defined order on such equations?
So when you do these expansions, you will see how they come out. It's a nice little it's a nice machinery, really, to derive the normal forms from something else. Yeah.
How do you know what exactly which equation to identify as a normal form, like between?
Oh, which equation? Oh, that is a hard equation. That's from if you have a one-dimensional system, it's obvious, right? It's the equation. But otherwise, you have to experiment with your example. If you have a bigger system, how do you know exactly in which direction is the parameter that is the bifurcation parameter? That's not the trivial issue, right? Because you might non-dimensionalize your problem, and then you can get the combination of parameters so that you can see what is the actual actual the combination of parameters. So that's can be a tricky task. Or so that's exactly finding the right combinations in a big system. That's not a trivial task at all. Yeah. So these are known as codimension 1 bifurcations. So you need one parameter in order to get the bifurcation. Then we will see the cusp bifurcation. We'll see in a couple of minutes. Then you need 2 parameters to get to that. So that's a codimension 2 parameter. Then you can add 3, 4, 5. So then it becomes. So that means you can. A lot of these branches come together with bifurcations into one. Yeah. So absolutely, you can have you can start multiplying these together and get all these coming together at the same point. Right? Absolutely, in principle. It's that can be pretty tricky. Okay, so now what I've really introduced is just the sort of
before you go further, sort of if I understand the motivation of this question, there is no standard machinery, mathematical machinery, to reduce an equation with several parameters to a normal form.
Yeah, there is machinery as such, but let's say you have a big system, right? Yeah. So to find so non-dimensionalize an equation, it's not always easy to find what combination. There is standard machinery, but I'm not saying it's not always easy. In mechanics, it's quite obvious because you have frequencies, you have these kind of terms you can sort of use. But if you have a combination of, let's say in economics, you have interest rate maybe on one equation, then you have something else. So it's not obvious how you non-dimensionalize something like that, yeah? Because what is, dimension means it's so different in some sense. Yeah? So I must say I'm not at all an expert in that aspect of it. No. But no. But
no, practically we very often face the problem.
Of course, of course, so it's probably very people who work in that. It's probably a very tricky problem. In a big space to find a direction that is the direction that gets you. It's not that easy if you have something bigger than 3 or 4 dimensions. Okay, so now what I've done really is to introduce the absolute, the sort of, I've squeezed in a lot. Typically I teach this in one term for my undergrads, right? So they do a lot of exercises and practice. So I try to squeeze that into you in 3 hours, which is a lot. So as I said, what I wanted to bring back home here is just the message that, even the simplest possible system you can find, you can see a lot of strange behavior, unexpected behavior, nonlinear behavior that you wouldn't have. So, and I've given you the basic bifurcation. So if you're interested, if you come across this thing, now at least you know what to look for, now in the literature, and where you can find it. So other transitions I've just listed here. Okay, so one is I will show a logistic map a little bit later. So there's something called a period doubling bifurcation. So what that means is that, so we have a periodic orbit or a fixed point in a map. So remember there was an equivalence between those two. We have the Poincare section and so on. So what happens is that the bifurcation point, instead, let's say the period is 5 seconds to come back. Suddenly you get a period that takes 10 seconds. So it doubles. So your normal 5 second period becomes unstable, and your 10-second becomes stable. You can also have transcritical and sub and supercritical in that case as well. So that is another thing that can happen. In the fixed point, as I said, I'll show you the logistic map. You have period 1, period 2, period 4, period 8, 16, up to infinity, and then you have chaos after that. So I will show that case as well. Another one is what is known as Neimark-Sacker bifurcation. That's when a periodic orbit transforms into a quasi-periodic motion, which is the torus I showed before, right? So you go from a periodic orbit to a torus. So that is called Neimark-Sacker. Sometimes it's called secondary Hopf, because you have a Hopf and then you have a Hopf of the Hopf kind of thing. You have a Hopf of the periodic orbit. So when you see these kind of motions, they sort of are almost periodic, but they don't really repeat themselves, but they are not chaotic. So that is an important distinguish between them. Okay? And then something I've touched, which I never teach to my undergrad at all, is our bifurcation that has to do with discontinuities. You know, when things happen very rapidly. So I'll just give a few minutes to that, which is a very active area nowadays. I will come back to the cusp, which is also the catastrophes, and tomorrow Vishu will talk about, you know, these kind of things. And so you have already noticed that a lot of this is about geometry and topology of surfaces and so on. So there are a number of other types of catastrophes that can happen that I'm not going to talk about here, and I'm by no means an expert in it. So that depends how surfaces are twisted and shifted around. Okay? So you can think of a saddle node as just a twist like that, and then and so on. You can see all these cubic equations and that. So these are just some of the changes that we can see, and people. And then there's also, I don't know if you've heard about canards. So there are these slow fast systems. So something that, as you know, the heart rate I showed in the beginning. So it's a slow for a while, nothing happens, and then there's a quick, really quick change, and then nothing happens, really quick change. So those are actually, it's another type of transition that has to do with that you have one direction where dynamics is really slow, another direction dynamics is really fast, and then some of them takes over, and then you get. But again, I don't have time to talk about it. You can, I'll just write it down so you can Google it and have a look. So they're known as canards, which is duck in French, I think. So because the first picture they plotted of this looked a little bit like a duck. I don't know. So that's that. So what I'll do next year is just to show a couple of these, what can happen in some of these situations, and then end up with the cusp by situation and the catastrophe there. Talk a little bit about good and bad catastrophes, as we already mentioned, that some are nice because you have a continuous change, some are not so nice because you can have rapid change. And then finish with examples till. So yeah, so this was the supercritical Neimark-Sacker and subcritical Neimark-Sacker. So you can see, so it's the same kind of picture. So mentally you have to sort of visualize these things, because once they start getting 3D and so on, it's hard to, you know, to draw a torus that is changing in 2D, because it becomes very tricky. So essentially what you have a period orbit, we have a bifurcation point there, and then we have quasi-periodicity instead, right? So if you remember this picture I showed for the, remember the picture I showed here? So we had the donut shape, so we have one periodicity around the donut and one periodicity in the small part, right? So two periods competing against each other. And so if the time it takes to go around that in that direction versus the time it takes to go around that, it's not a rational number. Then if it's a rational number, you get a periodic orbit. If an irrational number, you get a quasi-periodic orbit. So that's how it works. So if it takes one time unit to go around there, and then 3 time units to go around here, then it's a 1-3 torus or something like that. So it takes 3 periods, three revolutions to get around, and 1 for the whole thing. So if they're commensurate, then you get periodic orbit. If not, they are quasi-periodic orbit. So again, so this super and sub, that follows on all the time. So supercritical goes from period, goes to stable, goes to unstable, and the new stable is born. The sub, an unstable to unstable, but a unstable is born. So one is clearly much nicer to deal with than the other if that happens in a system, where here you have a continuous change from a periodic orbit to something that is almost periodic and just grows a little bit in size initially. While here, if you're on a stable path, you go here and you jump somewhere else because the instability. So the other one, which is, so if you have, so this is a phrase that was called, so this has been used lately for everything that where you have a qualitative change in your system due to discontinuity, either through those switches I talked about or an impact thing or something like that. If the qualitative behavior changes in whatever way, that is known as a discontinuity-induced bifurcation. And under that heading, there's a lot of different things that can happen. So I'll just mention a couple here. So one is, let's say that this is our surface. Do you remember we had some surface in space, and when we reach that surface, we have a switch or something like that. Okay? So assume that this trajectory now corresponds to a periodic orbit, a bit of a periodic orbit somewhere in space. So this, what we call in this world, we call this, when the two curves are tangential at some point, then we call that the trajectory is grazing. So graze means just barely touching. So for those so one can think of it as the relative velocity between the surface and the trajectory is 0, or the first lead derivative of the vector field of the surface with respect to the vector field is 0. So you can look at it from different perspectives. It's the same thing. So if we have this situation, then if we perturb this periodic orbit just slightly by changing a parameter, then two things can happen. One, we perturb it such that it doesn't notice the surface at all. Two, it hits the surface, and then we might have some rule on that surface what should happen, like before in the interest rate. Then, of course, the trajectory could go anywhere else. Right? So that is, similar. It's a silly example, but when Ireland decided to buy all the debt from the banks or however it works, that decision really changed the course of Irish history for a long, long time. That decision, and it's a similar kind of idea here, right? You hit this point where you go to different things, and so. And what can happen at these kind of situations is very, very interesting. Sometimes you jump to periodic orbits, sometimes you jump to chaos, sometimes you jump to nowhere. So very, very different things can happen. So if you Google that, you will be able to find a lot of interesting cases. Another interesting case is, so remember we had this other case when we have two vector fields on each side. So assume we have this very complicated case when the vector field on one side looks like that, the vector field on the other side looks like that. Right? So one situation could be if my trajectory comes in there, I hit the boundary, swap, and you can see the vector field on the other side is such that I just swap over, and something nice will happen. Nothing spectacular will happen. Another situation is if my trajectory is now on the other side, and now you can see in this region, the vector fields are pushing towards this surface. So that means somehow I will, what I call, slide along that surface. So that means my motion is constrained. So if you have some, if you have some, I don't know how to say this in a good way. So assume that you have, one way to think about this, assume you have T here, we have a boundary, we have another boundary there. So assume that we, every time we hit the upper boundary, we try to push it down. If you're in lower boundary, we try to push ourselves up. So that means we'll go up here, and then we will push down there, and then up here, and so on. Okay. So if you now let this be called delta. So what happens is that when this delta becomes smaller and smaller, then you get more and more rapid changes. And in the limit, you can show that in some cases, you actually get this sliding situation. So you can also see this as some kind of hysteresis effect if delta is positive, so that you swap back and forward in your policy decisions or in mechanics. It happens a lot, when you change the temperature in the rooms, everything.
This is a classic case of a class of business cycle models in economics. The floor and the ceiling.
Yeah. I've seen. That's right. Yeah.
And you try to then policy-wise reduce it.
Exactly. To this. Yeah. Exactly that. Yeah.
That's a classic.
Yeah. So do they do a lot of dynamic analysis on that, or this is just a conceptual thing? Yeah.
No.
No, they do. They do. Yeah. Yeah.
The first one is pretty simple.
Yeah.
And when you come to the pressing very close.
Yeah.
Then it's, but there are.
Yeah. Okay. Very good. So, yeah.
Sliding on the floor is economically intuitive, right? So if you hit the floor, you don't have, unless you have an exogenous push, you're not going to go up. Right?
No.
Slide.
Well, we'll discuss it later. That's not true. They're completely in the good win. First class.
But on the ceiling, sliding on the ceiling is
Both can be endogenously modeled. Realistic or not?
Yeah. So that's right. So these kind of things can happen, and if you swap this if you change the delta to very small, then you can have lots of switches, which is particularly in electronics and stuff. That would mean that your relay, whatever you're doing, is switching on and off all the time. And of course, it's not very good. And I suppose if you do policy, that's not good to change your mind all the time either, because the confidence will go down if you can't make up your mind about what to do. So, and then the third one here is very interesting. So assume we have this situation where the vector fields are pointing away in both directions. So you can see. So this is what is known as unstable sliding. So that means that at any point we can leave that surface. So this is a situation where you might have undeterminacy in a determined, fully determined system. Right? And that is purely because of the discontinuity. Which you can never see in a normal smooth system. But because you introduce this shift, this swap, it's potentially possible to slide here up to that point, and after that, anything can happen at any time. So people are starting to look at that, if you can think of that as a way to generate noise in a deterministic system, which is a really bizarre concept. So I think they'll start even trying to build some experiments to see if this is possible.
I want to ask you a very naive mathematical
question. Yes, please.
If your left hand and right hand derivative are not the same, if you take that as a
upper or lower, yeah.
What is happening? I mean, after a point you have drawn a continuous line, but
So this line that just corresponds to the surface where I have this switch. I have one vector field on one side, and it doesn't mean anything else than that. It just tells me where the rule happens. Yeah, and then somehow somehow you have to decide what do you do if you do get pushed into this. Somehow, and one solution which was by Filipov is exactly this, that you push this closer and closer, and in the limit you will get a sliding, right? But in some situation that could be you might not have a mathematically rigorous.
But defining the limit really becomes the problem.
Of course, yeah.
That is what discontinuities.
That's a mathematically not a trivial problem. Yeah. No, absolutely, yeah.
So you just make the band.
No, but so they have shown that in the limit, in certain situations, you do get sliding. Yes. Yeah. So what I'm just trying to say here, introducing switches in the system naively might cause dynamics that you wouldn't expect initially. And if you then simulate it with some tool that you have, and suddenly something happens that it's not picked up by your tool, then of course you're in trouble. And so, again, it's just good to be aware of things when you start introducing things in your models. And if you're not really aware of what they can do, then it can become a problem. So this is clear that in economics you do have models where you have switches from one region to another region. Right? So sometimes it's fine because you always end up just with a piecewise continuous in the sense that you just swap over to the other side and you don't have this pushing in situation. But potentially it could be. So you have to just be a bit careful. Okay, so that was the non-smooth. So final part here in the switches is to look at hysteresis and cusps and so on. So assume now, assume now that we have the situation, we have a saddle node bifurcation as before, or maybe I'll do it the other way around. We have a saddle node bifurcation as before. Here is our parameter that we allow to vary, let's say somehow vary, maybe in time or just varying it somehow. Okay, so what happens if that we have a stable situation, we move back here, and once we get to that point, dynamics slows down, but at some stage we get thrown down to something else, right? So assume now that that's something else. There's actually another equilibrium point there. So that's not unusual. In population models, for instance, the equilibrium point is typically 0, which means nothing survives, right? So all populations die out, for instance. So in some situations, that equilibrium point there could actually fold back on itself, so that you get, this is unstable, and then you get a stable situation like that. So that is not uncommon. So you have a saddle node bifurcation there, you have a saddle node bifurcation there. So when you so that means you swap down to that solution and so on. Yeah, so I'm just allowing A to vary, A is a parameter. So however you want, we can keep it like this, but I just allow it to vary somehow in my model. So now, well, parameters do their change in time. Yeah. Yeah.
The equilibrium is changing slowly.
Yeah.
At that point, when A moves a little bit,
yeah,
you're
falling down. You fall down there.
Drop down there, and as long as
so remember, your vector field looks like this, in the neighborhood. Right, so that's what it has to be by continuity. It has to look like this. So that's why it happens. No. I'll come. So next slide is hysteresis, right? So what can now happen in systems like this? If you now allow A to vary, we move up here, and then because the vector field looks like this, we fall down, and maybe we move further on along that path, but then we might turn. But remember, we're not coming back there because this is the stable one. But we go there all the way till we get another jump, but now to the upper level. So that means we can get these kind of hysteresis loops, which is also very common in a lot of systems. Yeah, it could be that's right. It could be a slow moving parameter, something like that, yeah. And here, of course, you can have noise in that parameter as we spoke about before.
previous slide, were you giving some example of that
the reason I use, so this is what it could look like. And the reason I do that, I'll show you, I use that for a specific reason. Yeah, but this is a cubic. So, there's 3 roots there, 1 root there, and 1 root there, right? So, So that means we have two folds. I should have done this picture a little bit better, but this is, in our case, it's an unstable part here, stable part here, and stable part there. But it could be the opposite, that we have an unstable part there, and stable part there. But then, of course, there would be no hysteresis because it would be an unstable situation, so we would go somewhere else. Yes? More? Oh, this one, yeah. The only assumption is we have one vector field here, one vector field here. That's the only assumption. Mm. Yeah, there's plenty of things that can happen. So you can have all the bifurcations and everything we have can happen even on this surface. We can have sets of equilibria here. We can have equilibrium points on the surface itself. We can have everything can happen on the surface. Depends on your model, how you're modeling it. So if you have some kind of damping in the model, then everything could die out and nothing could happen. So so everything can happen in this part, everything can happen in this part, and this is just a constrained part of the space. But of course, everything can happen potentially there as well. Typically, you try to model something. So of course, you don't have really that complicated motion on a constraint. But I guess in economics, you might have 50 or 100 variables. And it's constrained to a slightly smaller space because of this. Of course, on that space, you can have a lot of dynamics happening. The problem is, of course, because it's so complicated, so you don't notice it, in the real world. But of course, as the simple example of my hand and friction, then it's obvious. It's either moving or it's not moving. Right? But here you can see, if you want to be more abstract about it, so this is an equilibrium point. This is also an equilibrium point. So I have a whole set of possible equilibrium points here. So it's a bit, so it also, it becomes complicated from that point of view. But so you can land anywhere really.
In this case, if there is some small perturbation, depends on where you are pushed up.
In that case, yeah. So here, this is a very strange case that people haven't really started to look at properly. Last 5 years that it took off really to start thinking about those cases. Yeah. So that's interesting. So going back to this case, so hysteresis is something that happens in a lot of systems. That you fall down to something and then you overshoot that in the other direction. Then you jump up, then you overshoot that, and then you have this nice loops when it seems relatively nice and stable. So you can actually get periodic orbits of equilibria because you allow A to vary a little bit in time. But it could be very slow or could be very quick. So of course, the things you will see in ecological models, if this is indeed what happens in those rapid jumps, then of course this is in the scale of 100,000 or million, 100,000 year. Right? So something is slowly changing over time, and then you sort of move, and then suddenly your temperature goes up, and then it goes down. So potentially that could be, yes, yeah.
Recently, people have been talking. Suppose this is the economy.
Yeah.
It crashes from, let's say, high growth.
Yeah.
It crashes to low growth.
Yeah.
So people assume, okay, it's a problem of regulation. This parameter A is institutional. So we, do something, reduce the parameter A. But given that the set of policies related to reducing the A actually reduces the potential of the economy.
Mm-hmm.
So you don't actually go back to the original growth, but you go back to a lesser level of growth. Can that happen?
We'll see that in a minute. Yeah.
Okay.
I see what you're aiming at here. But this is, again, this is something you should be aware of, that hysteresis, that you not always jump up to the same level if you start moving a parameter backward, if you put it that way. But you can actually move up at some other place. And so on. A lot of material materials in mechanics works like that. You know, we squeeze it and then it doesn't come back to its standard the same form as before. You know, so you know, things like that. There are lots of this kind of histories. Electronics, it's very common. Okay, so notice now as a possible form for this fold is this. I should have plotted it more nicely, but I didn't. So I say that I've been varying letting B be some parameter, but now let's allow ourselves to also change B. What happens in that case? Okay? So that's when we get this. What for one?
If I look at it from this as the x-axis, it's like just A equals minus bx plus x.
That's right, exactly that. Yeah. So and B is just a constant. Yeah, yeah.
So those are the two.
A positive constant.
It is that.
Yeah, exactly that. Yeah. So then, if you now also see what happens when we vary B, that's when we get these. That's when we get these two. So this is, this catastrophe business. It's nothing more than just taking a piece of paper and folding it together. That's essentially what it is, right? So you have these two folds. Yeah. So this is a fold. So this is a fold, right? Then we have another fold. You have these two folds. And if I now rotate this paper like that, no, I'll try to. Yeah, so if I twist it like that, that's when I get, then I get the cusp point up on the top, and then I have two folds there and there. So what we had as a fold bifurcation was there and there, but now when we also allow ourselves to vary this parameter B, then we can see that the folding itself gets closer and closer together until they come together in one point. And then after that, if we do this carefully, after that you just get a nice curly surface, but something without any folds in it. Yeah? Like up here. Yeah. So that means now, which is what Raga was talking about before, right? So we can have a catastrophe fall back down there, but now the transition doesn't go back this way as before, up there. Instead, we're moving in this direction, and then we can come around back to the original setup and fall down again. So we have a smooth growth here to the original level, and then we have a rapid jump to a lower level through this catastrophe, if you want. Okay? So that means there are two ways really to come back to the same level, if you want. You can either go back this way and up and then go down. Yeah, that's right. So it's like a motion here, right? So I did it a bit crudely here, but it's essentially some motion how you change in your parameter world here, right? So maybe you want to say, you had something that you wanted to say about this. Yeah.
I can't imagine this. I could imagine the earlier one. Is it possible to show this on the piece of paper?
Yeah, I'll see. I'll see if I can.
Kind of.
So I'll see if I can.
That you don't come back to the same.
Yeah. So do you have one? I'll just get a piece of paper without the fold because it was hard. No, I understand. Raga and I were always discussing geometry. I sort of see it straight away, and he's like, "Oh, rotate it more." So we have two folds coming together like this, right? Yeah. So I'll try to. Yeah, I'll try to. One fold like this, one fold like that. Yeah, that's then they should come together in one point. So I'm not as agile as I should be. Yeah. So what happens is that you fall down there, and then you come around here and down again. Right? So this should be completely nice and smooth.
This is
Yeah.
the standard.
Yeah. So that's what.
This one is the
Yeah, that's the one. So you fall down there, and then you come up here and then round. Yeah, so here you have rapid jump downwards. So if you look at this in a time series, for some value. So assume we start there. We grow a little bit, then we jump down to this level, and then we have a slow growth up to this other level. And then, if you're unlucky, we fall down again. So this is the catastrophe. And then when I'm here, I'm moving up here, around, until I get to this point again, and then I fall down. So that is a mechanism that people have been looking at to see, is this indeed something that happens in reality? So remember, no, that's right. No, you might not have a periodic orbit, correct? Yeah, you might move, whatever you happen to be at that
Here
stage.
you don't come back. In this picture,
Yeah, here I do that.
imagine the pole. Then when you come back, it is not necessarily you are the same.
No, it's just a picture, unfortunately. It's a bit like that. But it could be that you fall down here or you fall down here, So absolutely. So that so that just increases or decreases the time in which this happens. The time length. What else was I about to say that? Yes. So as we know, at fold bifurcation,
To create all this, you require both A and B to raise in your original.
yes. So
normal algebra.
yeah. So this is actually the normal form. So, for the cusp bifurcation, in the same way as had for the other bifurcation. So that's why I use this form. So, so if you remember, one of the real part of one of the eigenvalues goes very close to 0 at the fold bifurcation. So that means that x dot in that direction is very slow because it's 0. That means that the motion here could be very slow, and that's something that people talk about, the critical slowing down. Okay, the critical slowing down of the system, and that's what people are looking at. And I bet tomorrow Vishu will be looking at this effect if you can indeed find them in economic systems as well as they have found them in ecological models, right, or systems. Looking at data. So you try to sort of see, is the dynamic slowing down just before the crash? So I don't know all the results there, but my feeling is that they don't behave the same way as the geologic systems. Because
They behave in every way, that's the problem.
that is true.
The problem is the opposite.
That's right. You probably get sometimes some of these changes and something else, because we haven't had too many of these crashes, so we don't have enough evidence for when one happens or the other. It's not enough to have 100 crashes in order to get some empirical understanding of what's happening, when there are so many different ways in which systems can vary or change or jump. So that's the hysteresis and catastrophes. And so if you then project this down on the AB plane, so then you get this very familiar shape. So if you project down the two fold curves there, similar here, that's when you get these kind of curves. They come touch. So here we have the AB space. So then we have a situation where we have the two folds coming tangentially together. And here we have 3 solutions, and here we have 1 solution, and here we have 1 solution. So typically in this case, we had 2 stable and 1 unstable solution. like here. Okay? 2 stable and 1 unstable. And that happens in that region. So this is also, if you look for cusps, you will see exactly that picture. Yeah. Now it's if you can, anything you can, any way you can simplify things like that. That's really nice to be able to classify things, and you can put it in the box, and that's nice. It lays there. Catastrophic for the field, yeah. Okay, so now the last bit here. So now we can think of transitions as being safe or dangerous, right? So, but the problem is, even looking at the transitions, you really have to look at actual problem to say whether a transition. As I said before, driving a motorbike, getting a Hopf bifurcation, and you get sort of oscillations. For the driver, it's pretty dangerous, right? But as a catastrophe, it might not be as dangerous. So, just looking at some of these. So we have been looking at some of these bifurcations. So remember the supercritical Hopf. We go from, so I'll draw some pictures here. So we have a stable equilibrium turning unstable, and then we have 2 branches of periodic, so we have periodic orbits here, okay? So that means if my solution lives here, right, and then it gets to this point, let's say you have it on noise, then depends on what the model is, I suddenly jump over to this. Okay. So one thing that could happen here is, of course, if your noise is big enough, so this is a sort of some kind of divider between those 2 branches. If the noise is big enough, maybe here, then you can actually jump down to the other attractor. Can happen if the noise is big enough. So that's the supercritical. So there you go from one branch to another branch, but continuously. So you don't get rapid jumps like in the hysteresis case. So the other one is a similar, I'm not going to talk about it. It's just going from periodic orbit to quasi-periodic. So it's exactly the same picture, but now this is a periodic orbit and this is quasi. Then we have the period doubling bifurcation, exactly the same. I go from period 1 to period 2, and so on. So you have a nice smooth transition, and even some non-smooth bifurcations, or DIBs as I call them, they can also have this behavior, but I'm not going to talk about this at all. So typical behavior, continuous growth of new attractor, which is this, just continuously growing out of it. No fast jumps to new attractors. If you perturb them locally, it's all determined, there's no complications, and no hysteresis effects. Right? And that's really, if you build a model, that's really what you want, unless you want hysteresis in your model. There are cases, but often you want things to happen smoothly. You can expect what to happen, even if it starts to oscillate. It oscillates just a little bit around where you were before, so it doesn't become very tricky to deal with. Okay. Then the other case is then the dangerous bifurcations, right? So that's where all the problems are really. Sudden node bifurcations, we have seen them. So that's when you follow a trajectory and then you fall somewhere else, right? All solutions disappear locally and you jump somewhere else. It could be that you jump to another solution or to minus infinity or something. Okay? The subcritical Hopf, so remember what that was. We have unstable solutions here. We had stable solution there, unstable solutions there. We vary this parameter. So again, if I'm on this branch here and I vary the parameter, then I might even go, once I get here, if I'm not exactly on this branch, then I go either up or down in this case. And then, so they going from a periodic orbit to a quasi-periodic is the same. Similarly, periodic doubling looked exactly the same. So you go from an unstable to unstable. So when you move in the other direction here, then nothing can, you might end up anywhere. Okay. So the dangerous thing are sudden disappearance of attractors, sudden jumps to new attractors. You can't determine what's going to happen when you perturb. You know, you might end up here or down there in this case. Also, the basin where your solution lives, they just become smaller and smaller. And if you have a bit of noise, then you get thrown out. So remember what the small basin is in this other case. Let's say we have, if you look at this potential thing that Vishu spoke about yesterday, if you have something like this and we have noise, a ball will move around here. But if we instead do something like this and we put in a little bit of noise here, then we will fall down that cliff, right? So the basin of attraction becomes much smaller when you get to a dangerous situation.
Is there again a standard mathematical mechanic in all these dynamical?
Oh, it's all geometry, yeah.
Of finding the size of the basin?
Ooh, general no. You will see some, I'll show you some basins in a minute. They are not, yeah.
That's one of the problems.
Yeah, oh, it's a big problem.
All this looks very nice.
It's a big problem, yes. Yeah, it's a big problem to find the domain of attraction for an attractor. Yeah, basin, up very hard. Very hard. You have to numerically do that. That's
all I need to know.
Yeah. Yeah. For 1D, not trivial, but easy, right? You can just, if you're able to find some potential surface like this, then you can see exactly what, then you can nicely put it together. But in the general case, no, it's tricky, very tricky. And then, of course, I said, you can also have this critical slowing down just before. So your dynamics is very slow here, and then you get the rapid change. So there are like two effects at the same time. Yes, so the last thing I'm just going to mention very quickly, because we have been talking a little bit about networks in this problem. So assume we have, so in this case, network of a human or a person. We can model him or her very easily with a differential equation. Could be a firm or anything like that. So that is, then we can use our standard techniques. Okay, if you're now putting these together to looking at them individually, no problem. It's just the system becomes bigger. But if we then start finding connections between them, then of course you have to, all of them have an inner dynamics, and then they have some coupling between them, right? Somehow, right? So you have define some adjacency matrix or something to couple. So this is already started to become a little bit more tricky game where you have dynamics on networks where they are not static. Okay, and then we can play this game, right? We have individual units of friends, they live their own lives, and you can sort of look at them. Then some of them start to connect into bigger and bigger societies, and so on, right? So to deal with this as a dynamical system becomes very tricky, right? You might have millions of units, and you want to sort of find something. So what happens, of course, a lot is that let's see if I had it in the previous. Yeah, so you maybe define some measure of, how do we try to understand maybe, the average age, if that's what we're looking for, or the income or something, and we try to merge, and then we do dynamics on that, try to understand. The problem here is, or could be, that so there are two things. In networks like this, as we've seen, you can have phase transitions, right, where maybe an opinion or something changes, in the whole population when you do some changes in some parameter. However, it's not clear yet how bifurcations on the individual level and phase transition on the global level, how that link is happening. if there is such a link and what it is. So that is still a nice open research problem. You know, how bifurcations on the micro level and phase transitions on the micro level through this middle level, how that happens. So that's a really nice question. So that is dynamics together with.
Are you assuming that it happens at both levels?
I don't know. I would be very surprised if the different individual units are somewhat similar, then they might have bifurcation, not exactly at the same time. So there is also, you know, because if you don't have, if they're not identical, of course, that's how you should approach this problem. Look at all identical first, just to see if you locally get some dynamics and in other places other dynamics and how it happens. So that's a nice little problem for the community to look at for the next 5 to 10 years. I think it will be looked at a lot. Bifurcations on local level and phase transition on the global level. So that's a nice problem if you're looking for some problems. And yeah, so that's. It doesn't, you know, so you can not doesn't have to. You can have dynamic, yeah.
Simplest case, even if it
yeah.
So you have this local unit connected, right? So,
Yeah.
So there are these small blocks there, and their interaction there could be in that. There could be a bifurcation.
That's right, yeah.
And you may ask the question based on this network structure, how fast that bifurcation effect may spread.
Yeah. There's a lot of interesting timescale issue and scaling issues and how that happens and. So it's a good problem. Yeah. So even if I've been talking about bifurcations that are well known and so on, there's still plenty of open questions out there. Particularly now when the network community and the network analysis have really, you know, started to become a real player in all aspects of science. Then it becomes more and more. Because if you can somehow simplify these things, then you can look at large networks and actually start asking some serious questions about things, which people already do, like we saw yesterday, some interesting results there. But you know, you take baby steps in this field. You know, try to understand some aspect, and then you build on that. So that was really, I just want to say something about that, because there is a lot of things still lacking, you know, in that understanding of small scale versus large scale that is not resolved in any way. So that is, it's very interesting. Okay, so what do we have? When do we finish? Half an hour. Yeah. So a few examples just to sort of motivate. Unfortunately, I have one example from economics and some from population dynamics. So the first example I would like to talk about, I'll say a few things so that we see. So this is the logistic map. Have everybody seen the logistic map before? Yeah. So basically, I'm not going to do all the analysis. You have it there, but essentially what it looks like is this. Right? So if we draw this in a map like this, if I have, what did I use? Xi here, xi plus 1. Okay. So you remember, if you're looking for fixed points, that means that xi is equal to xi plus 1. So you stay fixed to where we are. So that means that we can draw this identity line, right? Xi plus 1 is equal to xi. Okay. And then we can plot this map here. So that will look something like this. We have 0 to 1 here. Okay. Somewhere up here we have 1. So that means you have two fixed points here, one at 0 and one here. Okay. So then you can see the parameter a here, what that essentially does is just to lower or raise this. So if you have done this cobweb plots, then you can sort of see what happens. You know, we probably get some periodic orbit here. So we have a period 2 solution, something like that.
You have become an economist.
Is that what you do?
Unfortunate.
But is that what you do? But cobweb plots It's general. It's not only economy. It's a good tool anywhere. So what we're looking at here are two. So you can of course do the analysis, find the equilibrium, fixed points, find the derivative, and see whether it's between -1 and 1, and so on. But you can also do the cobweb plot and so on. Okay, so here I've done the analysis, what the solution looked like. But you see that one of these fixed points is 0 always, and one is varies with A. And that's obvious because if A is smaller, then of course the fixed point moves up and down. Then we can find the derivative and so on. And I'm not going to dwell on the analysis. You can see it there. But so if you now iterate this map over and over again in order to find all the stable motion. So here I vary A from 0 to 4. So from 0 to 1, the only stable equilibrium point is 0, and that is purely because A is so small, so it never crosses, the identity line. So there's only one solution there. And then once A is big enough, we get this nice branch of fixed points. And at 3 here, we have this period doubling bifurcation. So instead of, it swaps back and forward, back and forward, back and forward. And then it has another period doubling bifurcation back and forward. So we have 4, 8, 16, all the way up here. You can see infinitely many of these till you get chaos. And that is a very, very classical way in which you can get chaos in a map or a periodic orbit. It's a period doubling cascade to chaos, it's known as. So that is, I just want to show it out of interest so you can see some of these things that can happen. You can have these windows, self-similarity, and everything like that in this. So I'm not going to dwell on this. There's plenty of websites, books, and everything if you're interested to play. Stable, yeah. So this is stable fixed point, stable period 2 orbit, stable period 4 orbit, 16 orbit, and so on. Yeah. From this, that's the only thing that is needed. Yeah, so this is for the period 1. This is for the fixed point. But then for the period 2 orbit, you have to map this. If you map it to itself once, then you get the period 2 map. And then you can look at the period 4 maps. You can see that all these maps will have their own fixed points. So there's a big machinery here, which I didn't want to bring in here. But if you do the period 2 map, so you take the map of the map.
When you say period 2 map, it means xi.
No, what I mean by period 2 map is this: xi plus 2 is equal to f of xi. F of xi. So I map to myself after two times. Yeah.
Maybe if you just draw the picture.
Oh yeah, I can. That's right. Yeah, it will look something. What? Yeah. So it will look something like this. Can you see the red? So we have the identity line. So the period 1 map looks like this. Okay. The period 2 will look something like this. If I get it right, it will go through there. Something like that. Now xi, you map xi once, and then you map it once to get to xi plus 2. AI plus, the second iterate come back to itself. That's what the period 2 is. The second iterate comes back to itself. So if I look at this map, so those two, I should have done a different color. Unstable. I'll show you the next picture here. So this is what happens, right? So this is part of this branch. So this is the schematic. So this is the fixed point. It becomes unstable at that point. You get, and then you get. Yes, yes, yeah. The period 2 orbit becomes stable. So you get this cascade, right?
What I was trying
Yeah, I understand. Yeah. So you get this cascade infinitely many times. So you can see at the end here, we will have infinite number of unstable fixed point of all the orders of period 2 to the power of k, right? So that is what causes the chaos, as you spoke about yesterday. We have infinitely many of these, so we get thrown back and forth between these different fixed points.
See, what happens is, May has a classification. You have this one, and you have a 45 degree line, which is giving you two solutions. When you take a small value of a A, below 3, you just have 2 points. Then you have like this, small b, and the equilibrium becomes, that is what is called in period 2, and when you isolate yourself. Then it becomes two unstable ones. Then it again goes like that. Exactly.
Ah. What? Yeah, just get more and more of these wiggles,
And
right?
it becomes worse to put it in a two-dimensional diagram.
What is the fusion? I mean, when you are taking this period 2 and
Yeah.
maps, what is the
Yeah, so where it comes from is that the slope here becomes exactly minus 1. So, because then you are between plus and minus 1. So minus 1 is the point where you get period doubling. So then you get minus 1 there, it becomes unstable. And the new thing are born. And then if you do the period 2 map, then it also becomes minus 1. So you have exactly the same bifurcation happening over and over and over again. So it's just a fact of this map that it's like that.
The other map, Newton's method,
Yes.
that also generates, but not the same.
No, it's a different. I don't know too much about that, but it's not exactly the same. So because we're talking about noise, I just found this paper recently. I don't really haven't read it properly, but I found a couple of pictures. I thought maybe it's. Also, this is just the time history, so you can see what chaos looks like, but that's not very interesting. So here we have 2 bands, so we are one there and a band there, and then here's a big band, so we are up here somewhere, and this is just jumping back and forward between something. So you can see some regions you visit more often than others, and it has to do with the geometry of the map, what that looks like. So it's so extension of this, which I just saw recently. So don't ask me about all the details about the Wiener processes and stuff like that. But it's just in this problem, they took the logistic map and they added some very simple a noise term, and then some multiplied by some intensity, some variable. Okay. And so mean 0, variance 1. So the question is now, what survives and what doesn't survive? So I just found this picture. So in the original case, remember this is the first bit here up to 3, something like that. Okay? So the first bit, so the domain of attraction for this branch and this branch, it's all the white stuff here. Okay? And this goes to minus infinity, that goes to plus infinity. So here they've then plotted. So this is exactly the same curve as before from 0 to 2. But if you add that noise, the mean of about the equilibrium point actually goes down below in that case. And between that point and that point, all motion goes to plus or minus infinity, and then it picks up again. So you can see what
if you add the noise, then what happens? Stochastic terms, then what happens?
Yeah, exactly this, right? So this is what it looked like before. Right? And now it looks like this. Something goes to plus or minus infinity, and then it picks up again. So the noise throws you away, local to that bifurcation point, to outside the region of where the map is really defined. So it goes to plus or minus infinity. So this is a case where noise is really affecting a lot in the system. So I don't remember, yeah, so the noise here was 0.05. Or the intensity of the noise was 0.05. So I just wanted to highlight that we have talked about noise in other contexts the last couple of days. So So this is, so instead the mean of so of course there's noise about here, but the mean of the noise looks like this, then nothing here, it goes to plus or minus infinity, and then it picks up again.
So you have fixed the variance of the noise at 0.05.
Yeah.
Now you're changing the mean of the noise.
No, this is the out, this is what actually, if you actually simulate it, this is the, yeah.
So that dark line is 10, what is that, 10 times the mean?
Yeah, you know, as I said, I just saw it now, so I thought I'd bring it here. But it might be 10 times the mean, because it's probably quite, you know, small diversion away from the original. So that, yeah. But nevertheless, I find it very interesting that this transcritical bifurcation completely disappears when you introduce noise, and you get, you know, something very dangerous here, right? So you vary your parameter with some noise, and then you go to plus or minus infinity.
So where that curve stops,
Here, it probably this.
what is happening to the left of that?
Here, no, this is, yeah, so here you will have noise here, noisy solution with a mean around here. Here you will have noisy solutions with mean.
Oh, the dark line.
Yeah, the dark is the new. The dark is the new. The dark is the new noisy, mean of the noisy solution.
Noisy solution.
Yeah.
And so what is happening between that region where you have the dark?
So in that case,
The solution is just
it goes either to minus infinity or plus infinity. Oops. Oh yeah. So so it just means that the noise is pushing you outside the domain of attraction and brings you to plus or minus infinity. Probably minus infinity in this case, because you're actually, yeah, always minus infinity in this model.
suppose let's say R is 25
Yeah, there.
there, and X you start with 0.4. I mean the initial
Up here, yeah.
So then you
You
will
will go here and then you will oscillate down here.
there or the upper line.
No, I think this is just, they're just showing the standard deviation or something of the nose. Yeah.
So that, okay.
I think that is just some measure they've done there. So actually, I should have said that. Yeah, ignore the top line there. Just look at that. That's the only thing that matters.
So anywhere less than, let's say where the line drops off, you will fluctuate around that.
Yeah,
When
and
when
then
R is large, you will fluctuate around that. And in the middle,
you will disappear. Yeah, which is very dangerous in this. Yeah. So I put the link. You can find the
The
paper.
equation once more. I mean, it is just the
Oh yeah, it's just an additive noise there. I don't know magic, but so the next problem. Maybe I should show. Oh yes. I don't know. As I said, I just picked this up just recently because I wanted to show you, you know, how, because there was a lot of talk about stochasticities. You can look at the paper. I've you know, at the end here, it's all written up.
above that R level, it matches with that curve.
Oh, up to this. Then at least in the paper they didn't show more, you know. But then when it becomes chaotic, I bet you lose a lot of things again, because then you're so close to this +1 term, so you've probably been thrown outside this this stable domain, this bounded domain. So I thought this might interest some of you, this stuff. So maybe I'll show the Samuelson at the end here. Yeah. So yesterday Raghav mentioned the Samuelson Multiplier-Accelerator model. Right? So ignore my incompetence with interpreting exactly how the model works, but this is of course the standard setup that we have seen. In the beginning of the course, we saw this setup, and if you put all these consumption in the governmental expenditure, the investment, and so on together, we end up with this second-order difference equation that a lot of you probably, I don't know, do people study that in economics? Yeah? Do you? No? I don't know. Did they? Yeah, maybe. I don't know.
You look very uncertain. You haven't done it?
No?
Never? Difference equation you have never done?
And Samuelson, have you not looked at his models? No? Anyway, so using the same technique, so we end up with this equation here with the right-hand term, which is the governmental expenditure, and so if this is linear, second order, we can easily solve it. So M1 and M2 are just roots of this characteristic equation, so it looks like that. So we know everything about the system. So again, the roots here, which are essentially eigenvalues in the same way as we spoke about it before, matters. Okay? So then if you start looking at what type of solutions, which corresponds to what I did in the beginning of the lecture, when we looked at spirals, we looked at nodes and so on. So depending on, so a similar thing holds for discrete systems. So so there are boundaries between, so you remember we had, in the models we looked at before, we had these boundaries, we had the spirals, the nodes and so on, with the tau and delta. If we look at specifically this problem, then we can find those boundaries in terms of A and B. And if you remember, yesterday Raga showed this curve, so we have stable nodes, spirals, stable spirals, unstable node there, right? So in the same way as we've seen before, and I think so we have gone through all these roots and so on. Unfortunately, I didn't have any dynamics here, but you understand the principle. Remember now, this is discrete, so we are jumping around instead of going in a continuous curve. So that's the only difference. Okay? Yeah, those. Yeah, so this boundary tells you whether it's stable or unstable, and this boundary tells us whether it's oscillating or non-oscillating. With the eigenvalues essentially complex or real. And that's sort of, yeah. Maybe if you. So A, stable nodes, B, stable spirals, C, unstable spirals, and D. So I've written it in different ways there, monotonic divergence and convergence and so on.
System will monotonically converge to the equilibrium value of the system. If in region B, then it's going to be oscillate, but it's going to converge to the equilibrium value. In region C, that means the acceleration value is quite high, so that it is in region C. Then you'll have oscillations, but it's going to be explosive oscillations. And D is going to be explosive, so there's no oscillation, it's monotonic. So A was all the marginal propensity.
Yeah, so see, A is between 0 and 1, and B goes from 0 to.
On the boundaries, as you see the two curves on the edges between them, the boundaries of each region, the boundary between B and C, you have center.
That's right, here.
Diverging in between you have
the center. Yeah. So it's a similar setup, but specifically for this model. But I guess you can stretch it and change parameter and get exactly the same thing because it comes from the same. So interesting, so this is very linear. You can understand everything about it from the linear theory. So what Rag and I did was something simple, right? So if the economy is growing, so if t minus 1 is greater than t minus 2, we do nothing. We just allow the governmental expenditure to be the same. If the economy goes down, so I just swapped order here, then we allow a little bit of extra input from the government, right? So to boost the economy. That was sort of very simple, naive idea, right? And remember, a discontinuity like this is it's a bad nonlinearity. All these continuities are bad nonlinearities. Right? So just introducing this little extra thing changed, not everything, but it changed something. I'll show you here. So I do the analysis. I'm not going through that again. But, so that means in each of these regions now, where we have growth or not growth or not, we have one equilibrium point that exists in each of these two regions, right? So I can solve the second order differential equation specifically for G plus D and one without G. Okay, so yeah, so there are the two difference equations. So of course I can do exactly the same analysis as before. The stability will be exactly the same, but the position of the fixed point will change. So you see you have this extra term D. So nothing extraordinary exciting. However, if you now have two attractors in the model, that of course can start causing interesting dynamics. So I can't remember the parameters, but we have in one case here, we have starting with initial condition below this boundary, we end up with that boundary. If we start between those two boundaries, we actually have a period 2 solution in the middle between, and if we start above, we will decay down to the upper boundary. So just by doing that, we get 3 different solutions. I guess this is in region A, right? Yeah. So this is when this is where we region A is up here. Okay. And then so then I can't remember all the cases. So we could get period 2 solutions only in another region, and in some cases we could get something that looks like chaos as well. Yeah, so the only thing was that this line didn't so this didn't exist. So I just did an addition of some governmental investment or into the economy. Yeah. Yeah, some kind of stimulus into. Oh yeah, so everything else is the same. It's just the right-hand side that is changed. Yeah, that's just plus D or not. Yeah. So you know it's a very small change, but it leads to 2 different fixed points, so you can see them there. But also you get more dynamics between them because they're sort of fighting for it. So what we can see here is so I'm doing some analysis here. So this is what the fixed points look like. So the 2 fixed points lie exactly on that boundary. Right? So this is when we are in recession, and this is when the economy is growing. Right? Below that line, recession. Above that line, economy is growing. The fixed point will lie on this fictitious line that we have introduced. So that's an interesting thing, right? So we have this switch. The new fixed point for the economy will lie exactly on that boundary, and the period 2 solution will lie here, moving back and forth between them. Okay. And then I'll do more analysis. We're not going through that now, but now we can find the stable manifolds for them exactly the same way as I did 3 hours ago. Right? So the stable manifold for F2 are those two. Notice it doesn't exist in the other side because F2 is a sort of a consequence of the vector field, or the vector field up here. Similarly, F1 is a vector field of what's here, so this is the stable. And then we have this period 2 manifolds as well. Okay? So you can see we're starting to get a quite interesting picture here of how the dynamics changes. And this is more analysis. I'm not going through that, but I wanted to show this picture. So this is what the domain of attractions look like for the 2 points. So F2, everything here will eventually end up there. Everything up here will eventually lead up here, and everything in here will go to that period 2 solution. So because everything is linear here, we can analytically calculate all these lines and curves and maps back and forward, right? So you can see I've tried to show what these mappings look
So
like.
you are doing the small t, the government expenditure.
Yes.
You are treating it as a switch.
Yes.
You are putting it on,
Yes.
putting it on.
Yes,
and
yes,
on,
yes.
And you get this stable band in the
That's right. That's right. Which is a small period 2 solution. So that is the bad situation we spoke about before. On, off, on, off, on, off, on, off. So the government can't make up its mind, which is probably not, from a policy point of view, is probably not the most ideal behavior. But if you're strictly following some kind of rule, then this...
Actually, this is, what it is.
Yeah.
It is, you should not fine-tune the economy.
Yeah. Yeah. That's right,
If you do it too frequently,
Yeah.
stimulate.
That's right, yeah. Because this becomes very hard to understand what will actually happen, because you allow so many different behaviors in the solution. But I found it very interesting. You take a very simple linear model, you put in the smallest possible discontinuity, and it changes the game quite drastically in some cases.
Actually, the interesting thing is you don't change you don't change the characteristics.
No, not at all.
Everything remains the same.
Yes.
Simply, you are giving it the frequency of how you use
That's right, yeah. So, of course, that rule you can change and play around with as much as you want, right, and then do things. So I thought this could be a nice place to stop with a model from economics, finally, after a day of lots of not hard maths, but a lot of concepts. So hopefully you'll bring some of this with you when you continue all your studies in economics and dynamics and other areas. So yeah, thank you for listening.
Thank you. We did spend a lot of time.